challenge. All you gotta do is leave it better than you found it. It's gonna get difficult to stand, but hold your balance. I just say whatever, cause there is no way you're bound. Everyone falls down sometime, but you just gotta know it'll all be fine. It's okay. It's okay. It's okay. Feeling good, like I should. When in dark, I walk around the neighborhood. Feeling blessed, never stressed. Got that sunshine on my Sunday best. Hey, some days you wake up and nothing works. You feel surrounded. Gotta give your feet some gravity to get you grounded. Keep good things inside your ears just like the waves and sound it. And just say whatever, cause there is no way you're grounded. Everyone falls down sometimes. Welcome everybody to our 5-hour cram finale for AP Statistics. Josh and I am super pumped to be here. I hope you all have your Sunday best on. For me, it's gym shorts and a t-shirt because we're about to totally hop into this and we are going to kill AP Statistics today. We have so much going on, so many things that we have to hit, but we've got 5 hours. Get comfortable. All right, get you some snacks. I've got my water. All right, we ready to go. I'm probably going to go grab an Uncrustable at some times because, you know, what do you live off of in 2020? A whole bunch of Uncrustables. So that is where we're at today. I see we've got a lot of people joining us, which is fantastic. I'm so glad you're here. You are in the right place, and we are vibing with AP Stats today. So a few kind of ground rules before we really get started. If you have questions in about things going on, I know everybody does. Try to avoid putting questions in the Q&A right below your stream. Things like, are we going to cover blank? Will you go over blank? We are going to cover probably at least 85-90% of things on AP Stats. So save those questions for the end. If we miss something, then we can go over that. I just don't want to overload our TAs who are monitoring the chat today as we are really getting things going. Our TAs are fantastic. I've been working with Sander all semester. He knows this stuff for sure, and more TAs on board today as well. So I just don't want to overload them. So if you have a question about something that we're currently talking about, hit that up. But if you know, are we going to cover this? Can you go over that? Save those for the end if we miss something, because chances are we're probably going to go over that. Okay? All right. I am super excited. All right. So as always, the stream is being recorded in that chat down below, the Q&A. Just you know, if you put your name there, it will pop up on the replay. A lot of people might be catching it for the other app administrations. I might refer to a question if there's a good question in the chat as well. Okay, so put a more generalized question if that's something that or generalized name if that's something you're concerned about. Okay, all right, quick video from our founder, Amanda. So turn your attention to her for a second.
What up, AP students? It's Amanda here from Fiveable. We are literally giving away $100 to pay for your AP exams to like 50 different students. How do you win? Easy. You just gotta post about the AP experience on social media, on TikTok, Instagram, or Twitter. Use the hashtags YesWeCram and with Fiveable, and tag at Think Fiveable. So one person will win every single day, and this is how you can win. It is going to be a group of students who actually judge the winner. They will pick the winners, and this is how they're going to choose. It has to capture the AP experience. Do they look at that post and think like, that's 100% what this feels like? Is it creative? You know, is it funny? Does it have a really awesome song in it, or really good use of some sort of meme? Anything. Do we see creativity and engagement? How many likes do you have? That literally is going to help you win. The more likes, the more likely you are to win. And then finally, does it incorporate Fiveable? Is it in the caption, what you're wearing, in something that you're doing? how have you incorporated Fiveable into it? So this is how you can win. A couple of quick notes. Make sure you follow Think Fiveable so that we can DM you if you've won. You can post as many times as you want. You could post today, tomorrow, every day, as many times during the day as you want, but you can only win once, so keep that in mind. And finally, some of our best social interns came from this contest last year. So if you're really awesome at social media and you're looking for an internship, show us what you've got, because we want to hire you. So I can't wait to see your posts. See you on the flip side. Good luck on your exams. Talk to you later.
Whoop, whoop. So yeah, take advantage of that. That is a fantastic option. I'm already seeing some texts from my students who are super excited about that as well. Be creative. I would love for my TikTok feed, for the TikTok algorithm to figure out AP stats, and I would love to see all your videos on there. All I have to do is watch one. We know how TikTok works, right? So yeah, check out Fiveable on all the social media platforms. You're probably getting close to done with your exams, but there are way more resources on there for other courses if you're doing a later exam administration for some of the other courses. So I think every AP subject is pretty much covered, so take advantage of those awesome resources. So in this particular stream, all right, I could just say we're going to cover everything because we basically are. So we are going to spend an hour on describing univariate and bivariate data. Those are units 1 and 2 in the course exam description. We're going to do some multiple choice practice. We're going to do some kind of free response practice, okay? Then we're going to spend about an hour on collecting data. That is unit 3 in the CED. All right, multiple choice practice and free response on those as well. Probability, which is, as you guessed it, unit 4, with some multiple choice and free response. That's hour 3. Hour 4, we are going to cover units 6 through 9 in the CED, which is all inference. Inference for means, inference for proportions, chi-squared test, which is more advanced inference for proportions, and then a little bit of linear regression t-test on the very end. Maybe just a few multiple choices because it's not super common. So I want to, make the most of our time. That unit's not as big of a deal, but we will look at the basics for that. And again, multiple choice free response practice. And then at the end, we are going to wrap up everything for with doing some mixed review. I think total we're going to do about, I did the math earlier, about 30 to 35 multiple choice questions and 4 or 5 free responses. So that's almost a full AP exam. So lots of practice in here. You're going to get a chance for that as well. I'll get you all hooked over to the Mentimeter, which is how we're going to answer mainly multiple choice questions today. All right, so actually, yes, before we do that, those are the kind of the topics. So let's swap over to Mentimeter for a second, okay? All right, so you can join the code. It is menti.com, and you're going to use the code 60447339. And then I want you to move the sliders and tell me how you feel about those 4 topics we just talked about, okay? If you're like, oh, crap, I don't know, that's fine. All right, so slide it over there to the left. If you're like, yeah, feeling pretty good about that, then we will slide it to the thumbs up. All right, a few more seconds on that. I'm just going to say this is really cool watching these sliders on my screen change as you're seeing them as well. They all started at 0, and then as people started answering, those sliders started falling into range. And as more people answered, those sliders stopped moving as much. Okay, they might go from 3.6 to 3.5 or up to 3.7. And the reason why is because the law of large numbers, okay? As we have a larger sample size, it's not going to be affected as much by one number. So somebody could come in and say 0 on all of those, and it still wouldn't affect our number very much because it's pretty much already honed into that population mean for each of those 4 categories. So anyways, kind of seeing where we're at. To be honest, this is about where I expected everybody to be. I think this is kind of the generalized feel for where we are in AP Stats usually. Describing data, we usually feel pretty comfortable on. You've been doing that since August or September. Experimental design, you feel pretty good about that, okay? Again, you've been doing it for a while. And then probability is always the weak spot, which is totally, you know, it's always the spot that everybody's a little bit weaker in. And we're going to look at 3 or 4 different possible free response questions. That's usually going to be number 3 on the free response section of the exam. So we are definitely going to touch on that a good bit. Okay, and then inference, we're kind of iffy there. And a lot of that is probably because teachers ran out of time at the end of the year. I generally think that's mostly why that one's a little bit lower. So, yep, we are about where I expected us to be. So, good deal. So let's hop in to our first topic, which is describing data. And notice I put that at the top of the screen there, that it is 20 to 30% of the exam. So if you're feeling pretty good about that section, you probably can expect to see 7 or 8 of the 40 multiple choice, and then probably one free response. Probably number 1 will be from one of those 2 units. And then also number 6, the investigative task generally has something in it as well, mixed in with maybe a 1 part or so on the other free responses, okay? So the different aspects of a univariate, remember univariate means 1 variable, okay? So we'll look at bivariate a little bit later, which is more of the, more of like scatter plots, that sort of thing. But a univariate data distribution has 3 main components, okay? You have your center, which is going to be your mean or your median. It's always best if you include context on that first thing that you're writing out. So the center of my data is approximately blank, okay? The center room size is about 300 square feet. All right, include that context on that first sentence and you're good to go. Unusual features and outliers. Okay, remember that formula to prove outliers. You add or you subtract 1.5 times the IQR from the first quadrant or first quartile, and then you add 1.5 times the IQR to the third quartile. Okay, so those are that's that formula. It shows up a lot on the exam. Being able to prove that is very important. Shape, all right, it's either symmetric, skewed left or right, bimodal, you have the two humps in the data, or uniform, which means every outcome is pretty much equally likely. It's just a rectangle, okay? And you know kind of what symmetric is. Skewed right means that the tail is to the right, okay? And skewed left means the tail is to the left. So think about, whenever your data curves out, where does the tail go to? If the tail goes to the right, it's skewed right. If it goes to the left, it's skewed left. And last thing is spread. All right, spread might be the IQR, which is the third quartile minus the first quartile. You could use the range. You could just say the data is spread between 100 square feet and 400 square feet. That would be sufficient as well. Sometimes you might also use standard deviation. One thing to remember is that you can look at shape first, and if the shape is symmetric, then you can use mean and standard deviation, which typically go together as we get into inference and things like that later on down the road. All right, if your data is skewed, then the median or an IQR or median and range, or just saying generally spread out between these two numbers, is a better option. And the reason why is because the median is resistant to outliers. If it's skewed, there's a high chance there's an outlier way in one of those tails. And it would be inappropriate to use the mean because the mean is going to be affected by those outliers. It's going to be pulled in the direction of the outliers, okay? So we don't want to do that. So therefore, if it's skewed, we want to use median and IQR. If it is not skewed, then we can use mean and standard deviation if it's symmetric. Okay, typically mean and standard deviation are going to come into play when you're asked to describe a sampling distribution. And those are the formulas that you pull off of the formula sheet, which we will get to when we talk about probability a little bit later. So the best way to remember that when you're asked to describe a data distribution is to cuss the data. Center, unusual features, shape, spread. If you're asked to describe or compare distributions, then that is the steps you're going to take. Okay, and remember the definition for the standard deviation, that is the average distance from the mean. How far on average are all of our data points from the mean? Okay, so some different types of data distribution displays. All right, so here's one. That's a histogram, and it is the different percentages of cholesterol, distribution of cholesterol among people's blood samples, that sort of thing. So what I want you to do is in Mentimeter, all right, how would you describe that histogram that is up on the screen? It should give you some options of things you can put in. All right, I'm seeing a lot of great answers. I'm reading through them on my end on the Mentimeter. And in the beginning, we had just like some individual answers, which is good. I'm sure I'm seeing multiple people putting the same answers in. But here is where you are looking to cuss the data. Anytime you're asked to describe a distribution, describe a histogram, okay, what you're going to do is you are going to go through those four things. What I would say is this data is skewed right. Okay, that would be my shape. Okay, because you see, you have this long tail. You can barely see it. It's kind of like a bolded line to about 570 or so, where it just kind of like, trails off there. So I would say skewed right. If you cut off right here, I would say roughly symmetric. But I would say mostly skewed right, roughly skewed right, something like that, because there is those little bitty data points of people who have really, really high cholesterol. So shape, I would say, is skewed right. Now that it's skewed right, we would want to use median and either IQR or range, which is kind of hard to tell here. We don't really know numbers. We're just kind of going off the basis. So I would say the median is about 200, somewhere between maybe 210 to 220, okay, somewhere in this range. All right, where the median is going to be a little bit to the right of the mode, whereas the mean is going to be a little bit closer to the tail. So I would say somewhere right in here. So about 210 or 220 is the median. The median is about I would say the median the median cholesterol level is at about 210 to 220. There's my context. Okay. Also used a wiggle word. I didn't say the median was exactly 220, but I said it was approximately something. Okay. The only time you would use like an exact word, like the median is a particular number, you would have to know for a fact what the median was. And we don't really have a way of seeing that from this data distribution. So I would say that the median cholesterol level is about 210. Okay, so that's shape and center. I would say probably no unusual features because all of these are connected. There is somebody that has cholesterol somewhere between, the 350 all the way up to the 570. It's not like one person way on the end. Okay, it's kind of just a generalized tail. There's not a gap. Okay, so generally for an outlier, you would need that gap. So no apparent outliers. And you might want to make a note of, although there is a few individuals with the cholesterol level higher than 50, just to show that there are some way there to the right, but it's not necessarily an outlier. So there's that. And what was the last one we had? Spread. I would say the cholesterol levels range anywhere from about 110 to 570. All right, I wouldn't try to do IQR here because I don't know that. And I would just say that the spread is, it spreads between about 100 cholesterol to about 570 and just kind of generalize it there. So I used context and I went through my 4 CUS components. Okay, that is how I would go about doing that. All right, let's look at another type of data display. All right, this is the one that some people love to hate. It is a stem and leaf plot. And this is not any stem and leaf plot. This is a side-by-side stem and leaf plot. Okay, so now we're going to do sort of the same thing in Mentimeter. How would you compare the distributions from the Mets and Phillies? So we're looking at 2 sets of data here, the New York Mets and the Philadelphia Phillies, but no, Philadelphia Phillies. Not a baseball person. And also the number, also what would a key look like? So you could kind of add a little note. The key would be blah, blah, blah on that. Yes, and this is the number of home runs between the Mets and the Phillies. All right. In a season. All right. Let's see. Oh, I don't want to do. I'm going to do 30 more seconds on this, and then we will look at some responses. if you are having technical issues, all right, if you look down below the screen where the video is at, and you can, I think you can post a question on over there to the right. It says chat has been disabled. If you're experiencing technical difficulties, click here. All right, so if you're having technical issues, click over there. I'm seeing a few responses on that. Okay, all right, so first thing, let's look at the key. All right, so your key, swap my screen a little bit. All right, this one right here, okay, so key 1 line 4 equals 14. The only thing that's missing on that is that you would need to put the word home runs, some sort of context. So I think it's very common that you might be asked to create a stem and leaf plot on the exam. Okay, and if you were asked to do that, the key is necessary. And adding the key, just like this person has done here, is great, but adding the context is also important. Okay, so I'd hate for you to put together a stem and leaf plot and then miss the credit because of forgetting the context. Okay, so that's good for the key. Just make sure you put context. In this case, it's home runs. All right, good deal, good deal. This one's, I like this one here. Okay, both are skewed right. That is true. Okay, so if we look at our data now, it looks like one of them is skewed left. Okay, but remember they're vice versa. They're flipped. Okay, so there is most of the data is in the 0 and 1 category for both of them. Okay, and then as it tails to the right, which is the 50s, the 40s and 50s, is where it starts to slope down. So if you were to take those two data sets and put them both with a in a skew, then it would be skewed to the right. The tail would be to the right. Okay, so that is kind of the way it's, you know, sloping out, even though it looks like it's flip-flop, but it's really not. Okay, so they're both skewed right. The key is 1/2, 12 home runs. The median is about 20 for both of them. On this one, you actually could find the median pretty easily, and I would say we want to use comparative words there. So I would say the median for the Mets is higher than the Phillies. I wouldn't even put a number there. I would just say that the Mets has a higher median than the Phillies. Okay. Also, I would say the Mets has a larger spread than the Phillies. When you're asked to compare, you want to use comparative words on that. Okay. And the, let's see, outliers. Yeah, there's no apparent outliers between the two. Okay, so I would say that is what you want to do on that. Okay. All right. Good work. Good work. All right, and one more. So I will open that up on Mentimeter as well. Oh, nope. Okay, so I don't have a free response set up for that. So on this is a dot plot. So a dot plot is important to understand that every dot represents a type of data. Okay, so this dot over here at 2 means that that person took 2 minutes to eat breakfast. One person took 12 minutes to eat breakfast. So I would say maybe this one's bimodal, somewhere between 0. You know, there's kind of a mode at 0 and then another one at 10. There's a gap between 6 and 7. And, you know, there's a gap between 6 and 7 minutes to eat breakfast. The center seems to be at about 5 minutes to eat breakfast. And it's spread anywhere between 0 to 12 minutes to eat breakfast. Okay. So, you know, context on all those. The center is the easy one to get the context points on there. Okay. All right. So another thing to look at that is very important, it's a common type of distribution, is the normal distribution. All right. It is symmetric. It is unimodal. It is bell-shaped. And it is used to standardize scores or data value. So you can take things and you can make them fit into a normal distribution, and they all kind of fit in there together. And an important aspect of that is the z-score. So a z-score is where you fall on the normal distribution. Okay, and that is the average, or no, the standard deviation is the average distance from the mean. The z-score is how many standard deviations someone is from the mean. So either above or below. So if you're asked to interpret a z-score, make sure that you include above or below. The normal CDF function in the calculator will give you the probability of getting a data point greater than or less than some given value. So it's the most common distribution you're going to use. If you see in the prompt that something is normally distributed, what is the probability of XYZ? You're going to probably use normal CDF. We never use normal PDF. Be sure to label your calculator speak with your lower limit, your upper limit, the mean, and the standard deviation. So if you write those 4 things in the parentheses with normal CDF, label which one's the lower limit, upper limit, mean, and standard deviation for free response. That will give you credit. Also, it's a great idea to draw a picture of your normal curve, which we'll see in just a second, and label those things on there as well. If you want to find where a value would be at a given percentile, then you're going to want to use inverse norm. So if you know the area under the curve, so I know that, like, hey, I'm looking for the 70th percentile. That is 70% of the data is to the left of the point I'm looking for. Okay, then I can use inverse norm. So it works backwards. It tells me the limit, or the amount, the value on the normal curve when I know the area under the curve. Okay, again, label your your calculator parameters, your area to the left, your mean, and your standard deviation to make sure you get credit for that. Okay, and it's going to look something like that. You have your empirical rule, which is very important. 68% of the data is within 1 standard deviation of the mean. 95% of the data is within 2, and then 99% is within 3. Okay, that's the empirical rule. Sometimes you can use that to do normal distribution values, but generally the normal CDF is the easiest way to go, because it'll give you the same answers, and then you don't have to really remember that rule, but it does show up sometimes. All right, let's hop back over to Mentimeter and do some multiple choice review. All right. So the first question we have, all right, so hopefully you're able to see this, and I will set our timer. Actually has a built-in timer for 1 minute. Okay, and I'll probably, well, let's see. I'll start the 1 minute in just a second. All right, so I'm going to give y'all 1 more minute there. All right, 15 seconds, and then we'll kind of see where we're at. Which of the following must be true? So it's really important to read the question on that to make sure you all right, so most people said 3 only. That seems to be the most common answer. Let me see, I got to pull up the question back on my end. So A, set A contains more data than set B. That is not true. We cannot determine how many data points are in A. All right, so A, or Roman numeral 1 is completely out. Roman numeral 2, the box of set A contains more data than the box of set B. Again, we don't know. We don't know how many data points are in A or B. They could both have 5 data points. They could both have 500. One could have 5. One could have 500. We don't know. However, C, or Roman numeral 3, the data in set A has a larger range. We can tell that because the whiskers on the box and whisker plot are more spread out on A. So I would agree that 3 only is the correct answer on that one. All right, let's look at our second multiple choice. And I'll give you a few minutes to answer that as well. You typically have about 2.5 minutes per multiple choice question on the AP exam. It's 90 minutes and 40 questions. So. All right, and we'll open up the timer now, countdown, and we'll go over this one. All right, and that ends up our voting. So let's see where we are at. I would agree the student did equally well in each class. Okay, so if I pull back up the image there, so in chemistry, the average was a 75 with a standard deviation of 12. This particular student scored an 81. That is 6 points above the mean, which is half of a standard deviation. So their z-score would be 0.5, a positive 0.5, because they were 1/2 of a standard deviation above the mean. So then keep that in mind, and you could, scratch work out this on your calculator or whatever. Luckily, these numbers are pretty easy to match up. So the calculus final are normally distributed with a mean of 80 and a standard deviation of 8. And this particular student scored an 84, which is 4 points above the average, which again is half of a standard deviation. So since this was half a standard deviation above the mean in both chemistry and calculus, the student did equally well comparatively on both exams. So anytime you're trying to compare apples and oranges, that's where that z-score comes in handy. Okay, you can see how well they did comparatively for the two. All right, I think we got one more multiple choice, and then we'll look over at Unit 2. All right. So which of the following could be the median of waiting times in minutes? on this particular histogram. All right, I'm going to go ahead and set the timer. This one shouldn't take quite as long. All right, a few more minutes. All right, let's see where we are at. All right, most people are saying 7.25. All right, 2.5, if you look at the histogram, is all the way there in the mode. And you know the median is going to be a little bit more to the right. 7.25 seems totally plausible. 12.25 is a little bit too far to the right. It's more so probably where maybe the mean would be. Remember, the mean is always pulled more towards the tail. And then the median is kind of slightly to the right of the mode when you have a skewed right or skewed left distribution. 15, clearly again you're kind of you're kind of getting over there in the outlier range there, and then 17.5 as well. So your median is going to be somewhere there in the middle between 5 and 10, you know, a little bit to the right of the mode, but nowhere close to the tail, okay? All right, let's swap back over to our slides, and we will hop in to Unit 2, okay, which is bivariate data. This is a section that really just takes a lot of studying definitions, I feel like, and that's something that not very many of us like to do, unfortunately. We are going to look almost exclusively at linear regression models, okay? The biggest thing I can tell you is know the interpretations. I put a interpretations guide in the Discord channel. You can go back and find that. I think Sander has pinned it to the top, so you can look at those, make sure you study those. So here they are. So slope, as the x variable increases by 1, this is the slope for a linear regression line. As the x variable increases by 1, the y variable is predicted, big word there, predicted to increase by 27.2, whatever the slope is, okay? So we need to make sure, and think back to Algebra 1 or 8th grade math, Math 8, I don't know. Everybody's different because we're all in different states, but slope is rise over run. That's what you learn, rise over run, and your rise is the slope you're given, and then the run is 1, okay? So your rise is how much the y variable is predicted to increase, because remember that least squares regression line is a prediction. It is not a set in stone, we know it's increasing by this. It is a prediction based off of the data points, and the data points never fall exactly in line with our least squares regression line. So as our x variable in context increases by 1, the y variable in context is predicted to increase by blank units if there are units attached to it. All right, y-intercept, again, Algebra 1. When the x variable is 0 units, the y variable, again context, is predicted again, to be blank, whatever that is, okay? So predicted to be, 37.2 square feet or whatever we're trying to look at there, okay? So again, make sure context is there, make sure the word predicted is there, and then it's just your definitions for Algebra 1, okay? Rise over run, and then at your y-intercept, it's where the x is 0 and what the y variable is, okay? You need to know the R value / correlation coefficient. That's the same thing. You could be asked either one, all right? There's a strong, weak, or moderate, depending on 0.8 is kind of the cutoff for strong. Anywhere between 0.8 and 1, or negative 0.8 and negative 1 is strong. Moderate is between 0.5 and 0.8, okay, maybe 0.4 to 0.8. And then weak is anything pretty much close to 0. You have to note whether or not it's positive or negative, which is going to match the slope. So if you're given a computer output, you need to make sure that whatever the sign is for your slope, that's what you're going to match your sign with for your R value when you take the square root of the R squared, okay? And then it's always linear, okay? Everything we do is linear. If there is an R value being used, it is used for a linear regression model. There's no such thing as an R value for any other type of regression models. And the only ones we do in stats are linear, okay? Between X and Y in context again, okay? So 3 things, strong, weak, moderate, positive or negative, and then include the word linear, relationship between context of the 2 variables you're looking at. All right, your R squared, which is your coefficient of determination, that's the word and then the notation for it. Blank percent of the variation in whatever your Y context is explained by its linear relationship with X variable, whatever the context is. Okay, the other one, and this one's not very common, but I was going through some old tests or some AP classroom questions, and this one seemed to show up a lot, so I did want to include it. The S value in the computer output. That is the average distance of your data points from the predicted value, which is the line. So remember, the residuals is the distance from the actual to the predicted. All right, so the actual data point on the scatter plot to the regression line, what is that distance? So actual minus predicted, just like the z-score and t-score is observed minus expected, okay? Also AP, actual minus predicted, so that kind of helps remember as well. So that S value on a computer output is the average distance of all of the points. So you take every point's residual and then average them together. So a lower residual, a lower S value is going to be good for a higher R value. Okay, and always context, always, always, always include context. You can get a definition slightly wrong, but include context and still get partial credit. Okay, also remember that, like I just mentioned, the residuals is the distance from the least squares regression line. Actual minus predicted. Actual is the Y value of the data point itself. The predicted is what you would get when you plug the X into the least squares regression line, okay? A linear model is appropriate when a residual plot, so when you're given a scatter plot, look at it and look at the context of the problem. Is it giving you the residual plot or is it giving you the scatter plot? If the scatter plot looks like a linear pattern, okay, I guess I should go this way, then it is probably linear. If your residual plot shows a linear pattern with the dots, it is not a linear model. The residual pattern should show no pattern. There should be no pattern. It should just be points everywhere, an equal number above 0 and an equal below 0, because remember, those are representing how many points are above my least squares regression line and how many are below. So we should have kind of an equal span. Also, there shouldn't be fanning. It shouldn't start all close to 0 and then span out as you go to the right. They should all be equally scattered, okay? So pay attention when you're given something that looks like a scatter plot and it says, is a linear model appropriate for this? If it's a scatter plot or a residual plot, there's a big difference in how you would handle that and how you would answer those. Okay, also remember to include context and a hat on your Y to show that it is a prediction. So if you're asked to write a least squared regression line, I would not use X and Y, I would use the name of the variables. So height with a little hat for Y equals 2 parentheses weight plus whatever, instead of X and Y. Okay, use the context for X and Y, and then on Y, Since it's the dependent variable and we don't really know, our line is we're using our least squares regression line to predict the answer, we want to put a hat over that. Okay, so here is an example of a scatter plot. Okay, so we got our points and we got our line going through it. And here's our equation. They messed up. They should put a hat here. All right, that's one little thing to point out there. Error. So the slope is 0.735. It's the one with the X. On a computer output, the slope is the one on bottom. Okay, the slope is the bottom row. So you'll see like coefficients, and then the bottom coefficient is the slope. The top coefficient is the y-intercept, which is the one that's not going to be put with X. Okay, let's hop back over to Mentimeter and practice some more on those. So here is our first multiple choice question we got there. Okay, a little bit hard to read. I apologize for that if you're reading it off of a phone. Let's try this. I think I can make it a little bit bigger on the stream part of it. Yeah, maybe that'll help. Also, you can zoom in with your, if you're using a phone, you can pinch and zoom. That's what I just did. You can actually click the picture too. Okay, so like on my phone. Okay, so on my phone, I clicked the picture for ABCDE, and I can zoom in and read it pretty easily. Okay. All right. I'm gonna set a timer now for 1 more minute to answer that. All right, voting is now closed. Let's see where we're at. Okay. Oh, I was on the wrong window there. Let's see. All right, so most people said E, which is the correct answer. Okay, in this case, the y-intercept, but we're not using y, they're using C because of the context of the problem, is negative 94. All right, you can see that from the equation. Negative 94 plus 0.9h. And it doesn't make sense to have a negative y-intercept when that is, the collar size. You cannot have a collar size of negative 94 inches. Okay, so that one just doesn't make sense in the context of our problem here. Okay, so yep, the answer was in fact E. All right, let's move on to the second one, number 2. We are looking at 20 professional athletes, and it tells us there's a strong linear relationship. Which of the following is a reasonable value for the correlation between the number of hours they exercise and their resting heart rate? All right, so let's see where we're at on this one. Most people said negative 0.87. All right, and that is correct as well. We're doing a great job on the multiple choice today. So, all right, so if there's a strong linear relationship, it needs to be close to 1 or negative 1. All right, so 0.71 is probably out, although that's kind of close to the strong, so that could make sense. 0.0, that means no correlation, so that one's out. Negative 0.14, that is a weak correlation, that one's out. Negative 0.87 sounds good. And then negative 1 would literally be a perfect correlation, perfect negative correlation, which is not very likely. All right, so you pretty much can narrow it down to 0.87 just based off of the fact that it's a strong correlation, but not going to be perfect, okay? And it does say, for those who exercise more hours, have lower resting heart rates. So as one variable goes up, the other one goes down. That is a negative correlation. One goes up, the other one goes down. That is a negative correlation. Therefore, our R value has to be negative because our slope of our least squares regression line is negative. So in that case, it has to be a negative R value. So A and B were out, 0.71 and 0 were out. And then the only one that was really strong but not perfect is the negative 0.87. So that was the correct answer there. All right. So now some free response practice. Okay. And I'm going to give you a little bit more time on this one. Okay. I'm going to give you, typically on free responses, you have 12 to 13 minutes. I am going to give you about 9, just so we can kind of stay on track here a little bit and get on to collecting data. But no, you typically have a little bit more time on that. Okay. So I am going to go to my timer up here at the top and set the time. You can go ahead and start working on that, and then we'll look at your responses. It's broken up into 3 parts, and you can just kind of answer them in one text box as best you can typing. I know it's hard to add some things typing, so do the best you can, and we'll look at some responses and talk about the things you would really need to include in your response based off of these. Okay? About 3 more minutes left, guys. All right, y'all, 30 more seconds and we will close this up. Whoop, there goes our timer. All right. So let's see where we are at. Okay. So the first question, I have to pull it back up on my phone. What is the equation of the fitted regression line? Okay. And we are predicting height on the amount of detergent. Okay. So the y-intercept for the height, so yes, height is the y. So I really like this answer, this response right here for A. So predicted height, down here we also have height with a hat. Height hat, oh my goodness. And then our y-intercept is negative 2.679. Notice how that is the constant coefficient. Okay, so if you're looking at the computer output, which you can kind of see over here, for some reason that's showing up strangely. It is the y-intercept is the first value available, okay? And then plus our slope, which is 9.5, and I would say amount of detergent. I really like the second response here for that, okay? So by using my, instead of using y and x, I put it context within my y and x for my regression line, okay? And also the y has to be predicted. So really good down here, okay? some partial credit here for sure. We need an X with the slope. Make sure the slope has the X with it, and also there's no context, so that would be probably would be a P if you had the X on that one. EPI kind of thing. Here's another one that's really good, but missing one thing, and that is that the height is predicted. Okay, I would put detergent in parentheses too. It just looks a little bit better, but that's probably just a personal preference. But the height is predicted, so great options there as we're kind of working through that, where Y is predicted height. This is another way of doing it. Just write out the straight up Y equals mx plus b. Again, we need x there. And Y is the predicted height, and X is the amount of detergent. Okay? So that is the first question. The second question is, note that S is 1.99821 in the computer output. Interpret this value in context of the study. That means that the average distance of points from the least squares regression line is the 1.998. I sort of see that there in a few responses. Let's scroll on down. We got plenty of people we can pull from. The average distance of data points from the predicted value is 1.99821 milliliters. That's good because there you're putting a little bit of context in there. So that's good. So again, standard deviation is just like standard deviation of anything. How far are you from the average? And the least squares regression line is your average. Identify and interpret the correlation coefficient. This one's a bit tricky. All right, so what you want to do, okay, is you want to take your R squared value, not the R squared adjusted. Anytime you get a computer output, just X that off. You're not going to use it, okay? Just not necessary at all. So X that off, and then take your R squared value, and then you're going to take the square root of it, okay? So in your calculator, I'm going to take the square root of 0.969, which is 0.984. So your R squared value should be 0.984, all right, which is positive because the slope is positive. The slope is positive 9.5. So therefore, our R value is also positive, and it's going to be positive 0.984. Okay? So you have to kind of find that. You just take the square root of the R squared, not the R squared adjusted, and that gives you the R. Okay? And then if that's a really high R squared value or R value, so that means that there would be a strong positive linear correlation. So this student right here, the correlation coefficient is 0.98. 984 is fine either way, which means there's a strong linear, make sure you include positive, correlation between amount of detergent and height. Okay, so then you got to have that context in there as well, between what and what. All right, and then you're good to go. So that is how you find the R value. That is what the how you take the R squared and go to the R value, which is pretty common. And they kind of work hand in hand, as you've probably seen before. Okay, let's flip back over to our slides. All right, and this is the same problem. I should have given you the context of the whole problem here. I forgot about that. But you really can answer everything from the computer output and the scatter plot. Okay, but this is the actual prompt. It gives you a little bit more context as far as the height of the soap suds and the amount of detergent. I'm sure you were all very confused about where height comes into play for detergent, but it was talking about the height of the soap suds, not the height of, you know, a person or something like that. So the same questions, and that's what we have, what we just went over. All right, so let's take a little brain break because that is the end of the first unit. So we will look over in Mentimeter. I think I have a fun little question for us to answer. Rate your favorite casual place to grab a burrito. Moe's, Chipotle, Del Taco, Taco Bell, Qdoba. Which one's your favorite? Oh, man. Oh, Moe's hopped out to an early lead. And I was like, what? Yeah, this is what I expected. Everybody loves Chipotle. Everybody loves Chipotle. But does Chipotle have Baja Blast? Didn't think so. Didn't think so. But apparently everyone still loves Chipotle. If Chipotle had Baja Blast, that would be something else. However, meh, they don't. All right, I'm proud of Taco Bell. Okay, they were an underdog. I wouldn't know if I would even say they were casual. Okay, but they are in second place behind Chipotle right now. That is pretty phenomenal. I've never eaten at Del Taco. I just saw that online that it was a popular casual place to get tacos and burritos and things like that. So I put it on there. I'm happy that some people actually are using that option. I have eaten at Qdoba. It's pretty good. I've eaten at Taco Bell way more times than I can count. I would say Moe's. They got the Coca-Cola Freestyle, which has Diet Barks root beer, which is no longer in production, which makes me really sad. And I can get it at Moe's. And I like their food more than Chipotle. Sorry, guys. But then, I mean, Taco Bell, though, that Baja Blast, man, some good stuff. All right. Man, now I want a burrito, okay? Unfortunately, the Uncrustable I had planned is, not is not a burrito. So maybe next little break we have while y'all are working on a free response, I'll grab an Uncrustable. That's all I got. All right. Awesome, awesome, awesome. So we'll keep that in mind. And let's move on. All right, this unit I think we probably can get a little bit back on track and finish this one by 3 o'clock Eastern Time, 2 o'clock Central Time. So this next unit is on collecting data, which is on the experimental design, all of those definitions. A lot of people really hate them. However, once you really get the hang of it, like it kind of makes more sense. So I feel good about that section as we're kind of moving into it. And to be honest, okay, the most important thing when you are designing a study is to make sure that you have a random sample. There's no fancy math that you can do to fix the fact that you have a biased sample. All right, and it's the thing that irritates me the most when I say, well, have you done your research? Have you read this article? Have you seen this study? And then you read the study and it's complete crap because there's not a random sample. You ask people that you wanted to ask a question that would give you the answer you wanted. Okay, and that's just crap. It's one of the big things in like the data analysis community right now. It's called p-hacking. Basically, you can get funding for a study or whatever, and if you can make a study where your p is low enough, then you can get the funding and you can get the money and you can get published, which is what everybody's after. However, what people are doing is they're making samples that aren't random. They're hacking the p-value to make it get what they want, and that's just like, totally against the integrity of statistics. You cannot fix the lack of randomness when you're sampling. So if you don't take a random sample, you might as well just stop there. The rest of your work is useless, okay? And the reason why that's important is because that ensures that we can make a generalization of our findings to our population. That's called the scope of inference. You take a big population and you pull out a few people in a random sample, has to be random, and you can study those few random people. And then if you get a really interesting outcome from those few random people, if it was large enough and if it was selected randomly from that population, you can generalize the results for that sample to the entire population, which is the beauty of statistics. You're taking a small amount of people you can work with and making a broad brush picture to the whole population in which you want to make findings about. Okay, but it has to be a random sample. Again, that's called your scope of inference. So if you see something about scope of inference, you want to make sure that the people you pulled your sample from match the population you're making a claim about from your findings. Okay, so a few ways of creating random samples. Sometimes that's what you're asked to do. You're asked to either randomly assign treatments, which works the same way, or you're asked to randomly sample 50 people from a population. The first way you can do it is a simple random sample. You can do what I always refer to as the hat method. You can take every person in the population and you can put their names in a hat and you can mix them up. You have to mix them up. That's where the random part comes into play. And then you can draw out however many you want. Okay, if you want a random sample of 50, you put all the names in a hat, you mix them up, you draw out 50 names, and that's your random sample. Another way you can do it is through a random number generator. Assign every person in the population a number between 1 and 550. Use a random number generator to generate 50 unique numbers, skipping the repeats. You don't want to have one person drawn twice. That wouldn't make sense. And then those 50 people are your random sample. Okay, so that is how you are going to select a random sample from the population. That's just a simple random sample, just like the normal basic. Another way is a stratified random sample. A stratified random sample is when you separate your population into meaningful groups. Separate your population into meaningful groups and then draw maybe 5 from each group. Okay, so you have 5 groups and you draw 5 from each group. That's 25 total. That 25 is your stratified random sample. Think about Skittles. If you take Skittles, a meaningful group you could put a bag of Skittles into is by color. You could take all the green ones and put them in a cup, all the yellow, all the purple, all the red, and all the yellow. I think that's the 5 colors. And then let's say you took 2 Skittles out of each cup. Well, now you have an equally set up random sample where every color is equally represented, and that would be a stratified random sample. You take basically 5 small random samples from each group that were, meaningful groups, and then those little small random samples make up your stratified random sample. So they're separated into meaningful groups. Okay? And then next is a cluster sample, which is very similar. A cluster sample would be like taking a bag of Skittles, dumping a little bit into one cup, a little bit into a second cup, a little bit into a third, a little bit into a fourth, a little bit into a fifth, and then I just select one cup. Okay, so I select cup 3. So after I have 5 cups, I put numbers 1 through 5 in a hat, mix them up, draw off the number 3. All right, so all the Skittles in cup 3 is my cluster sample. So they were separated into equal groups, but not meaningful groups. It was just, like off of a production line, fun-sized bags of Skittles. Those are a cluster sample. They just take all these M&Ms and put a little bit into a bag, a little bit into a bag, a little bit into a bag. And then whenever you get your little fun-sized bag of Skittles, you are receiving a cluster sample from that whole production. All right, because you're getting a little bit of each color, but it's not totally balanced. A little bit here, a little bit there, a little bit of difference between the colors. Another type of random sample is a systematic random sample. That would be something like every 3rd Skittle off of the production line gets put into a bag. Okay, so there's a system in place to make sure that things are split up evenly or whatever. So every 3rd sample, people coming, you want to ask people who come into prom a certain question, and you ask every 4th person that comes in the question. Okay, that's systematic. Now, that's a little bit biased unless if you're asking something about prom, because you're only taking the prom goers, not everybody in the school. But then again, that depends on your scope of inference. If you're wanting to find something out about the prom goers, then sure, that's fine. Okay, you're asking a random sample of people who are at the prom a question about prom. But if you want to find out the consensus from the whole school, you can't just ask people who showed up at prom. Okay, so stratified, here's kind of a diagram to kind of show that. So we separate them into group 1, 2, 3, and 4. Red, yellow, blue, and green. Everybody in group 1's red, everybody in group 2's yellow, green, and blue. I took a simple random sample from each group, and those together made my stratified random sample. Okay, again, think colors of M&Ms. I separated them by color, took a little bit from each color, boom. That mix of a little bit in each color is my stratified random sample. All right, cluster sample. All right, I took my population and I just told the first group of people, all right, y'all go into group 1. And then some more people came in, you go in group 2. Next group, you go in group 3. You go in group 4. All right, notice those groups are all equally balanced. All right, some blue, some green in each group. It's just kind of randomly separated. And then I would take the numbers 1 through 4, put them in a hat, mix them up, draw out a number, and say I get number 3. All right, well, this group of 6, since it's from cluster number 3, is my cluster sample. I take everybody from that group that I select. Whereas a stratified sample, okay, I don't take everybody from group 1. I just take a few people from group 1, a few people from group 2, 3, and 4, and then together those 4 groups of a few people make my one stratified random sample. Whereas cluster, you take everybody from that cluster. Okay, you separate them into groups, and that whole cluster is your sample. Okay, that's really a big difference between those two things, is that whenever you're separating into your groups, stratified, you take a little bit from each group. Cluster, you take one group completely. All right, clearly when you're taking samples, bias is going to come into play. An important part of designing any type of study is to reduce bias. You have to make sure you do that. Making sure you pull a good sample is one part of that, which we've already sort of talked about. Response bias is another thing. The way your question is asked or worded can prompt a particular response. You generally don't want to do that. You want to ask it the question in a non-biased way. So for instance, like in my home state, because of COVID, they have made lunches free for all students as sort of a COVID relief. That might be nationwide, I'm not sure. And it would be first of all, it would be show a lot of lack of compassion or whatever, but it would be very biased to ask this question about free lunches in a way of maybe the COVID pandemic has caused a lot of kids to go without food due to parents losing jobs. A lot of students depend on this free lunch to achieve, to gain their nutrition. Do you think free lunches should continue? Well, any person with any bit of compassion would say yes to that question, okay? And hopefully we would. But that's the way that's worded is a very biased way. You're kind of tugging at the heartstrings a little bit and saying, oh, these kids all could depend on it, which clearly I think we all would agree with. Yes, you should continue that in the times we're in. But adding that part in the beginning totally would make someone feel guilty for saying no. Now, if they do say no, maybe they should feel kind of guilty, but that's beside the point. That question will be worded in a biased way. You also could bias it the other way. We see that all the time too. All right, nothing in life is really free. Free lunches are costing taxpayers, blah, 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 blah. Should we continue school lunches at the expense of taxpayers? You see things like that, and it kind of makes people think, well, maybe I should say no, it shouldn't be continued. Because it's worded in a way that's drawing out a certain response. It also could be asked by a particular person. All right, if a policeman comes up to you and says, have you ever used illegal drugs? You're probably going to say no, and I hope you all would say no, truthfully, but you would be more likely to say no to a police officer as opposed to someone who one of your friends. You would be more truthful. So that's also another type of response bias, when the person asking it is prompting you to probably say yes or no or whatever. All right, so non-response bias in the way the sample was chosen. Volunteers is always going to create some type of bias. Make sure you indicate, if it says, if you're given a problem where volunteers are involved and it asks you to discuss the bias, make sure that you clarify which direction the bias is going. All right. Since we're taking volunteers, it's going to sway people more in this way, to the left or to the right, or however. Okay, also, sampling could leave out a group of people. Going back to our prom example, if you were asking a question about the whole school body, and you only ask people at prom, where you're leaving out the group of students who don't go to prom, and that's also problematic. So that would be under coverage. Again, that would be fine to do that systematic random sample if you were asking something about prom. You don't want to ask the non-prom goers about prom. They're not there, okay? But if you're asking about something generalized to the school, you would want to not leave out the non-prom goers in that. So that would be an example of undercoverage. Just depends on what population you're focused on, and make sure your sample matches that. Okay, experimental design. This is huge. This is the golden rule of statistics. I can almost guarantee you that there will be part A or B of a free question that will ask you this slide right here. The difference in an experiment and an observational study is that an experiment has treatments that are randomly assigned to the participants. All right, and it is treatments of the explanatory variable. You need to clarify, don't just say it's an experiment because treatments were assigned. That's only partial credit. This is an experiment because were assigned, which clearly that's unethical. It's just the first thing that came to my mind. But you want to clarify what treatments were or were not assigned. This is an observational study because smoking cigarette treatments were not randomly assigned to participants. All right, so that random assignment means that it's an experiment, which is going to change things later on today when we get into the inference section as well. Okay, observational study, they are not randomly assigned. The researchers are not interfering with the participants in any way and saying you get A, you get B. All right, an experiment they are. An experiment is a much stronger study because then you can say that there is causation involved. All right, explanatory variable causes response variable. You cannot say that with an observational study. All right, so I call this the golden rule of statistics. You have to have that. Be sure you understand the difference in this and explain it in context. All right, it's very easy to say this is an experiment because treatments were randomly assigned. That's going to be partial credit. Which treatments were randomly assigned? It could also be asked in a way of, the results tell you that something causes something. That word causation should also cue you that it's an experiment, okay, if they're telling you causation is part of it. And then you could, same thing. It's an experiment because treatments were randomly assigned. Connect those dots as well. And again, which treatments are randomly assigned? All right, so different parts of a study. You need to be able to identify your variables. All right, what is your explanatory variable? That's typically your x-axis. That's your independent variable. What is your, also with an explanatory variable, a little side note here. When there's more than one variable being measured, those variables are known as a factor. Each value of a given factor is called a level, and each combination is called a treatment. So let's say you're testing water, schedule, and fertilizer for a set of plants. All right, and you want to test no water, a little bit of water, and a lot of water. And you want to test no fertilizer, yes fertilizer. Okay, so there are two variables. So the two factors in this are fertilizer and water. All right, now water has three levels. A little bit or none, a little bit, a lot. Okay, so there were three levels for watering. There were two levels for fertilizer. All right, yes fertilizer, no fertilizer. So then the combination of those, there would be 6 combinations. Those would all be the treatments. Those would be the treatments you would randomly assign. So you would have 6 total treatments. No water, no fertilizer. No water, fertilizer, yes fertilizer. A little bit of water, no fertilizer. A little bit of water, yes fertilizer. And then a lot of water, no fertilizer. A lot of water, yes fertilizer, which clearly is probably going to be the best for that. So yeah, so the difference is there. The factors are the different variables. Okay, the level is how many each variable has. And then the treatment is actually the combination of those things. So there'll be 6 possible treatments in the instance I just went through. All right, then you have your response variable. That would be the growth of the plant. Okay, we have 2 explanatory variables that we're creating within our treatments. And we're going to create the 6 treatments for. And we're going to see which of those 6 treatment groups is going to produce the most growth in a plant. And then you have confounding variables. Well, what about the weather? What's going on in the weather that could affect it that we're not really accounting for because we can't control? Okay, and how are we going to reduce the bias from that confounding variable? Making sure that each plant gets the same type of weather. Put them in the same greenhouse, okay? And then you have the 4 components of a well-designed experiment. You have to compare at least 2 treatment groups. Sometimes that's a control group and the the treatment group, control and treatment. Sometimes it's multiple, like what I just went through. That would have 6 treatment groups. The control group would be the no water, no fertilizer group. All right, you have to randomly assign treatments. I have to put all my plants into a bucket, pull out 2 at random to go to one treatment, 2 to each get the 6 treatments, and they're equal. Okay, each group gets, or each treatment has an equal number of plants. All right, there has to be more than one experimental unit in each group. That's replication. A lot of times in science, we think replication is being able to do the experiment again, which is true, because then if you're doing the experiment again, you're increasing your sample size. But replication in AP Stats is really more focused on a large sample size, that we can be sure it wasn't just because of random chance one plant died with the water and fertilizer just because it was a bad plant. And then number 4, we have to control the confounding variables where possible. So if there's a confounding variable, we have to make sure that that is controlled in some shape, form, or fashion. All right, how are we reducing bias from that? All right, let's hop over and do some multiple choice on Mentimeter. All right, so here is our first question. An observational study found that the amount of sleep an employee gets each night is associated with job performance. The correlation coefficient was found to be 0.86. A reader of the study concluded that more sleep causes employees to perform better. Why is such a conclusion not correct? All right, I see where we're at. Looks like most people have probably answered. Got several answers in. Observational study. You did not randomly assign treatments, therefore causation is not a thing. You can say correlation, all right, and that's what we have. We have a correlation coefficient, but we do not have causation at all. Okay, let's move on. Okay, I think maybe we're having some issues going offline and online. I don't know what's going on there. I'm trying to chat with the people on the other end and see if we can get that straightened out. So we are looking at a chemical being applied in 2 doses to different cell types, A and B. Each combination of dose type and cell type was to be replicated, decided to use 4 lab technicians. One technician will be assigned the high dose with strain A. A second will be assigned the low dose with strain A. The third will be assigned high with B, and fourth low with B. The assignment of lab technicians would be randomized. A statistician told the researcher that the design could be improved by controlling confounding variables. Which of the following is a confounding variable on this study? Okay, so let's see what our options are. All right, so we are controlling the different doses and cell types. So most are saying lab technician. And I think that would be the correct answer as well. So the lab technician, you would want to make sure you control that. And so yeah, you are randomizing them, which is good. You're not giving one lab technician the treatment that they really want to give or whatever. Could be a little bit different. So you would want to make sure that they are trained in a way that is equal among the two. So like in educational studies, and you have multiple teachers teaching different classes, different ways, you want to make sure that that the teachers are teaching equally. They're trained to equally do things. So one class is not just going to do better because the teacher was better, but the teachers are equally trained. And that's really hard to do. Same thing here with the lab technicians. Okay, so let's move on to the next multiple choice. More laundry detergents. We have lots of soap and laundry detergents today. Manager of a public swimming pool wants to compare the effectiveness of 2 laundry detergents, detergent A and B, in cleaning the towels that are used daily. As each dirty towel is turned in, it is placed into the only washing machine on the premises. When the washing machine contains 20 towels, the manager flips a coin to determine whether detergent A or B will be used for that load. The cleanliness of the load is then rated on a scale of 1 to 10 by a person who does not know which detergent was used. The manager continues this experiment for many days. Which of the following best describes the manager's study? Let's see. Let's do 30 seconds on that one. All right. Let's see. I'll extend it a little bit more. It's like a handful of people are still trying to vote, so. Hopefully that opened up back voting for you. I think it did. All right, so let's see where we are on this one. This one's a little bit tricky. Okay. Yes, it is completely randomized design. Awesome. So this is not a block. This is not a block design because we did not separate it into blocks. Blocking in an experimental design is almost like stratified random sampling in a way. Basically, you are doing multiple experiments within your major experiment. This were block design. You might want to say washing machine A and B. So I'm going to take washing machine A, randomize detergent A or B. Washing machine B, randomize A or B. And then that would have been the random block design with washing machine as the block. But we basically were only controlling one variable, which was the detergent. Okay, we were not separating into another smaller variable and performing an experiment multiple times. Okay, I wasn't doing in the randomized block design with detergent A and B as blocks is very close. It sounds right, but I'm not randomizing anything within detergent A. All right, I didn't say, all right, this one's detergent A, which washing machine does it go in or something, okay? The detergent is what I was randomizing, but it wasn't what I was blocking for, okay? And then it's not matched pairs. Matched pairs would be if you were to wash every towel with A and then judge it, and then every towel with B directly after that and then judge it. So everybody would receive both treatments. That's not how we did that one there either. Okay. All right, so the next one. All right. Oh, I gotta pull it there. In the design of a survey, which of the following best explains how to minimize response bias? How do I minimize response bias? Hopefully peer pressure isn't getting to you on this one. All right, looks like we are all pretty much in agreement. Carefully word and field test survey questions. That is the correct answer. Okay, so increasing sample size and randomly selecting the sample, that would help to minimize non-response bias. So remember, response bias is things that want to pull out a particular question, particular answer. Okay, and the wording of the question is going to more so be the response bias. The sample size and the randomly selecting is going to minimize the non-response bias. Those are the sampling bias types of things, okay? But yeah, so we want to carefully test carefully word the questions and also field test them to make sure they're not going to prompt a certain response. Okay, I think this is our last multiple choice. Under which of the following conditions is it preferable to use stratified random sampling rather than simple random sampling? All right, I'm going to agree with the majority on this one, okay? First answer choice, the population can be divided into a large number of strata so that each stratum contains only a few individuals. That would be very cumbersome to have 100 different stratum that then you're pulling 2 from each group of 100. Like that's not very preferable to do, okay? It's not very easy. Answer choice 2, the population can be divided into a small number of strata so that each stratum contains a large group of individuals. Well, what's the point in separating into 2 groups with 500 apiece? Like that's going to be randomized enough just through a simple random sample, so it's not necessary. Answer choice 3, which is the correct one, the population can be divided into strata so that the individuals are as much alike as possible. So now the individuals in each group are very much so alike. Therefore, we can balance out these groups that are alike. Okay, think colors of Skittles. Okay, I can make sure that I get an equal representation of those colors of Skittles. The population can be divided into strata so that the individuals in each stratum are as different as possible. Well, that's not what we do. We put them in groups that they are alike with. The population can be divided into strata of equal sizes so that each individual in the population still has the same chance of being selected. That one seems correct because you do want to make sure that there's an equal chance of being selected. But that wouldn't really mean the equal chance of being selected is more the simple random sampling, not preferable for the stratified random sampling. Okay, so that one is not going to be it. All right, so here is our free response question. Okay, so the first thing to do, you have a golf course using a mixture of lime and 2,4-D, which is a type of fertilizer, to give their fairways nutrients and prevent weeds from growing into their grass. And then it gives you kind of the breakdown of the problem. So the first thing is to list the treatments for the study below. And I will set a timer for this one. It's 3 parts. Let's do 3 minutes a piece on our timer here. Okay, so now 2.5 minutes. All right, about 33 seconds left, you all. There's that awful sound again. All right. So let's see where we are on part A. All right. Oh, computer's thinking. It's thinking real hard. There we go. All right. So our treatments, all right, are going to be, this is very similar to the question we looked at. There are 6 different treatments, and we need to list them all out very explicitly. So like this response right here is great if we were only looking at the lime mixtures, the 0, 5, and 10. However, we are also looking at the 2,4-D, which is 0 and 10. All right, and I see a lot of people saying 3 mixtures of lime and 2 features, or 2 mixtures of the fertilizer. Okay. Let's see if we can find one. This is kind of weird because they're both in the same context. All right, this one, I think I like this one here. Yes. Okay, notice there are 6 total treatments there. 0 milliliters lime, 0 milliliters 2,4-D. 5 milliliters lime, 0 milliliters 2,4-D. 10 milliliters lime, 0 milliliters 2,4-D. And then the 0 with 10, 5 and 10, 10 and 10. All right, so that is the best way to answer part A. You have very clearly all 6 treatments, the things you're going to be randomizing. All right, a lot of people listed out the factors and the levels for those factors, but it needs to be very explicitly clear that there were 6 total treatments because it asks for the treatments. And this is the way you would list that out, okay? Every combination of the 2 factors with the multiple levels, okay? So we had 2 levels for one, 3 for the other. 2 times 3 is 6. You should list out the 6 treatments. And you can even number them 1 through 6. Treatment 1, treatment 2, treatment 3, treatment 4, treatment 5, treatment 6. Okay. Let's move on to part B. Same question, part B. You can answer on this one because I really hope they're good on this one. I'm going to do 2 minutes. All right, and we're going to stop it for the timer yells at us because I know we don't like that. And let's see what we got here. Computer's still thinking. All right. This one right here looks fantastic. I love this response here. This is an experiment as the treatments of lime mixture and 2,4-D mixtures are being randomly assigned to regions of the golf course. All right, bingo. You got context. It's an experiment. That was the correct answer. It was an experiment because they are randomly assigned, and we are randomly assigning the lime 2,4-D mixtures. Okay, so that is perfect. You got what was being randomly assigned. You mentioned the random assignment, and of course you said experiment. Those are generally the three things for that part B that is very likely you see tomorrow for that particular topic. Okay, great job, everybody. Great job. All right, and then part C, last one, part C. Describe how the golf course manager would randomly assign the treatments to the 24 regions on the course. And I will give you all 6 minutes on this one. Probably requires a little bit more thought and a little bit more typing. So I'm going to set a timer for 6 minutes. And we'll reconvene in 6 minutes. And there's our timer that everyone loves to hate that nasty noise. So let's hop on back and see what we got. Awesome, awesome. Let me pull up the correct windows. All right, let's see what everybody had for part C. All right, so one of the big things here is if there are 24 sections of the golf course and 6 treatments, we need to be sure that each treatment is given to 4 sections. 6 times 4 would be 24, okay? We want to make sure they're equally done. So I like this one. This is a great start here. Label each region of the golf course 1 to 24. Put each number in a hat. All right, now when you put them in a hat, you need to mix them up. All right, think the little lottery ball thing. You know, I like sports, and when they do the lottery drawing for draft picks, you know, they twist the little thing, and then they pull out the ball, and it's always like the team that everybody has this conspiracy of. Oh, they always pick that team. Okay, I know there was the deal with the NBA. I can't remember what team it was that they got the shaft, but you know, there was a huge conspiracy that it was rigged. That it wasn't really randomly assigned, and I think they kind of found that to be true. I think it was the Knicks. The Knicks were involved with it somehow. But so you put each number in a hat, 1 through 24, and then you're going to, you know, mix them up somehow. You got to randomize them that way, and then assign the treatment chosen with the random number region given. So what I would do is I would draw out 1 to receive the first treatment, treatment A, if you labeled them that way in part B or part A. Then draw out another number to also go to treatment A, and continue doing that until each treatment had 4 sections. Okay, 6 treatments, 4 sections to make 24 regions. Okay, so that's a really great start on this particular response. I would make sure we mix up in the hat, and I would also make it clear that each treatment has 4 regions. Okay, but definitely some good stuff there. So here somebody had randomly assigned every one of the 24 regions to the 6, I wouldn't say experiments, 6 treatments. Okay, it's only 1 experiment. Okay, I think this could work. The golf course manager would assign a number to each treatment, 1, 2, 3, 4, 5, 6, and then roll a dice at each of the 4 regions. The number that is rolled is the number of the treatment that region would receive. That is good. However, we do want to make sure each treatment is repeated. There's that replication coming in. So I would add to this, once one treatment has at least 4 regions, it cannot be used again. So then ultimately by default, each treatment would be at 4 regions. Okay, but the dice is a good way to randomly assign it. Here we go. Golf course manager would assign each of the 24 regions a number 1 through 24 and randomly draw 4 numbers from a hat to assign to each mixture of the lime and 3,4-D or 2,4-D, whatever, and do this 6 times for each mixture. Okay, so instead of numbering the treatments, you're going to number the regions, and you're going to say, okay, here's treatment A. Also work really well. Okay, so just kind of the key things there. Make sure it's randomly assigned somehow. That's where the mixing in the hat goes into play. Make sure that each mixture is going to get 4 regions because there are 6 mixtures. That in the past, questions like this were graded on that. And yeah, and then context in there as well. The hat method's good. I saw some random as long as you're clarifying that it's random and each group is getting an equal number of the treatments, okay? Or each treatment is getting an equal number of golf regions to compare with, okay? That random assignment is going to account for the fact that maybe some grass on the golf course is in the shade, maybe some is not in the shade. We know that's going to be a confounding variable. That could be a part D. What would be a confounding variable in this? The amount of golf course in the shade versus the amount of golf course in the sun. kind of balancing that out, which the randomness here should do. All right. Okay. Now we're moving on to probability, which this is also going to have sampling distributions mixed into it. So we're really looking at more like 30% of the exam, 20 to 30% instead of 10 to 20. But sampling distributions is also kind of split with inference. It bridges the gap between probability and inference. But the just raw probability questions are more so 10 to 20%. So what that is, finding the odds of something happening. What are the odds of it raining at my location? That was a big TikTok trend. Oh, geez, when was that? I want to say back in like January, February. 40% chance of rain means that there's a 40% chance that rain will fall somewhere within like a 50-mile radius of the location you're asking about. Doesn't mean that it's going to rain 4 times out of 10 in your location. That kind of threw people off. So yeah, that's what probabilities are. So some calculate probability tomorrow on the AP Stats exam. Two-way tables, which we'll look at some examples of. Density curves. That's a normal curve typically, that you're thinking normal CDF here, all right? Other density curves, yeah, sure, they're in the course, but it's not a huge topic. The main density curve you would have is a normal curve, a geometric curve, or a binomial curve. And I guess technically the chi-squared curve and the D curve, a p-value from those two types of tests are also density curves. Area under density curve is 1. We'll get to the others in the inference hour starting after this one. Random variables. You could have a binomial random variable. There's 4 conditions we have to check for that. We could have a geometric random variable. There's 3 conditions. One of those is different from binomial to check for those. So those are random variables that you might have given some certain verifications. That it falls into a category that is used for two-way tables and categorical values. Okay, so the percentages, proportions, and means as you get into other things. Okay, so here's an example of a two-way table. This is that doesn't give raw numbers for the amount of middle schoolers taking a car or a bus or other, but it gives a percentage. Okay, so you can use, it works either way. The probabilities are calculated the same way. And let's see if I have some questions off of this for in the Mentimeter. I can't quite remember. I do.
Your Google Home isn't set up yet. To get started, download the Google Home app on a phone or tablet.
Nice. All right, so let's see. Let's hop on over to Mentimeter and let's look at the two-way table that we have here that you can see up on the screen. All right. Oh, I think I gotta change the slide on that. So what is the probability of a randomly chosen person being in high school? All right, so that is the first question from this. What is the probability from that two-way table that you can see on Mentimeter? It's the same one I had on the last slide. What is the probability of being chosen to be in high school? All right. Hopefully you got 0.58. So if you're looking at that remember, this type of two-way table is giving us the percentages. It's not giving us raw numbers of how many high schoolers. So it actually makes the work a little bit easier. 58, if you look at high school, the total number for high schoolers was 58. And then normally if it were raw counts, you would divide that by the total, which is 1.00, which is 100%. Okay, so 0.58 divided by 1, which is 0.58. 58% of the individuals in the study were in high school. All right, so part B, what is the probability of a randomly chosen person taking the bus and all right, so the probability of randomly choosing a person taking the bus and you're going to take that one cell and divide it by the total. And in this case, we would have 0.12 divided by 1.00, which is the total on that end. Okay. Let's see if that will come back up for everybody. All right, it looks like it's back on my end where I'm answering questions. So hopefully we're good to go here. All right, so yes, so looking at our two-way table, 12% took the bus and we're in high school. Now, we want to take the cell that's and high school and then divide by the total, which in this case, since it's percentages, is 100%. So 0.12 divided by 100% is still 0.12, okay? If it were raw counts, though, you would have to divide by the total for an and probability. Okay, and then C, what is the probability of a randomly chosen person being in high school given that they take the bus? All right, this one is a little bit different here because we have a conditional probability given that they take the bus. And really the main thing I'm doing with Mentimeter now is so that you can see the questions and the two-way table on your phone you can refer back to. I'm not really looking at your responses in Mentimeter, but it allows you to have more, be able to see it in more than one place. All right, so this one, all right, so whenever we have a conditional probability, we are only focused on given that they take the bus. We are only focused on that bus column. So everything else is irrelevant to us. So we're only focused on that one column. And the ones that are in high school is 12%. So 0.12 divided by the total bus, because we're only focused on the bus. So this one we're not dividing by the total, we're just dividing by the bus total because the bus is the condition that we're only interested in. 0.12 divided by 0.26 is 0.462. So of the bus takers, 46% of them are in high school. All right, what is the probability that someone is in high school or takes the bus? So high school or takes the bus. There's a few ways you can go about doing this, but you'll come to the same answer either way. All right. So one way to do this is take the total number of people in high school, which is 0.58, and then to add in the people who take the bus that are not in high school, which is the 14%. So 58 plus 14, which is 0.72. Another way of doing that is you can add up the two totals, the total high school and the total bus, which would be 0.58 plus 0.26, and then subtract the overlap. We don't want to add that 12% twice. So 58 plus 26, and then subtract the 12%, because we counted them as part of our high school 58 and as part of our bus 26. We only want to count that 12% of students once, so we want to subtract that from our total. And we again land at 0.72. Okay, so just basic probabilities and conditional probabilities. That's how you would do it from a two-way table, if it's by percentage or if it is by raw counts. Now, if you're given a problem with percentages, a lot of people think, oh, I need to do a tree diagram, which you can. That's a great way of doing it. However, I'm more comfortable with a two-way table. So now, I hope we are back now. We had to swap our streams over, and I think we're good. It looks like it's showing back up for me on my extra computer that I'm answering Q&A on. So I think we are back, kind of dropping some of the graphics to make sure we can get things streaming and on the right track. So we were looking at the two-way table on the Mentimeter. All right. So I'm seeing that everybody can hear me. I'm seeing captions. I'm seeing that. So we were looking at how to calculate probabilities from the two-way table. You should still be able to access it from the Mentimeter. And we can see one thing you're going to need to be able to do besides just calculate probabilities is also be able to determine independence from a two-way table. Okay. So are the events high school and take the bus independent? Justify your answer. Okay. And what you would do there, all right, if you're looking at your two-way table, the probability of being in high school is 0.58. The probability of being in high school, given that they ride the bus, which is what we did in part E, is 0.462. Those two probabilities are not equal. Basically, you are more likely to take the bus in middle school than you are in high school. Therefore, those two events are not independent. So what you're going to do is you're going to compare two probabilities, the probability of an event happening and then the probability of that event happening under the condition that the first event, the other event, the second event is also happening. So the probability of A, is it equal to the probability of A given that B is true? If that's the case, then the events are independent. In this case, those two probabilities are not independent, and therefore they're not independent. And you have to prove that by giving some sort of comparing two probabilities. If they're equal, they're independent, meaning you're not more likely to ride the bus from high school or middle school. They are equally split up proportionally, or in this case, they're not independent. Okay. So that is how you prove independence, and that's a pretty common question to show up from two-way tables. All right, as we mentioned, and I did see it in a Q&A as well, you can take percentages that are typically used for a tree diagram, and you can put those together to simulate 1,000 participants. Okay, you can simulate 1,000 participants, or you can do like the two-way table that we have and just write them in percentages into your two-way table. And instead of doing a raw count two-way table, just do a percentages two-way table. Now, you might still have to divide some numbers for conditional probabilities, But you can just divide 2 decimals instead of 2 whole numbers like you would if it were raw counts. So we kind of touched that. So for example, if you have a blood test for streptococcus is found to come back positive 5% of the time, that means it's going to come back negative 95% of the time. Of the positive tests, 10% of those are false positives. Of the negative tests, 90% of those are true negatives. You could put together a full two-way table based off of these percentages instead of doing a tree diagram. All right. So you have positive, negative, true, and false on your rows and columns. And then from there, you could fill in the totals. The total under positive would be 5%, 0.05. The total for negative then would be 0.95. And then along that positive row, you would do 10% of the 5%, which I think would be 0.005. And then that means the rest of those are true positives, which would be 0.045. And then same thing with the negative. You could fill out that two-way table. So you could do it by percentages, or you could just do it by simulating 1,000 people, kind of like I've done here. So we said there's 1,000 people total. So if it's positive 5% of the time, 5% of 1,000 is 50. So 50 out of 1,000 positive tests. That means that 950 have to be negative. All right. So then of my 50, 10% are false positives, which actually should be under not sick. So I need to edit that real quick. See if I can change that. I don't want that to be wrong. Kind of a big deal there. 45 and 5. There we go. Present. Wow, I'm making my computer work really hard today. Really, really hard. All right. And I want to make this in full screen. All right. So, yep. So that is a way you could go about doing that. Hopefully that fixed that percentage error there. Yeah. All right. So then another type of probability. So moving away from two-way tables is when you have a normal curve. All right, that will be generally be given. It will state that it's normal. It will say the distribution of this is approximately normal. And your you will use your calculator to do that. I can pull up mine in a minute to do that. I'll have to kind of figure it out because I had to drop one of the software I was using, but we can figure that out. Shouldn't be too bad. Okay, so if you see normally distributed in your problem, and then something like what is the probability of blank or greater or something like that, you're going to use the normal CDF function on your calculator. All right, so here's an example. What is the amount of IQ scores are normally distributed with a mean of 103 and a standard deviation of 2.4. What is the probability of selecting someone with an IQ score, I know this is not right, of 95 or less? All right, so here is how that would look in the calculator. Okay, I'm getting the hang of this now. So I would go second, distribute, normal CDF. We never use normal PDF. My lower limit is negative infinity all the way to the left, negative a bagillion. My upper limit was 95 because I want to find the area under the curve from negative infinity to 95. My mean was 103. My standard deviation, we said, was 2.4 based off of what's given in the graph here. And then I paste it in, get my answer. Okay, and oh, okay, this was, no, it shouldn't matter. I did something wrong, or this graph is incorrect or something. Let's see, what did I do wrong? Maybe that percentage is correct. Oh, standard deviation is at 2.4. It would be 5.4 because it's from, I did it from 100. I'm sorry. Kind of flustered here with the technology, having to back up and punt. Not 5. 5.4. There we go. There's our 6.9%. Okay. This one's a little bit different. 6.94, 6.92, same difference. Okay. The AP College Board's not going to count off for 3 decimals being different. Different calculators give slightly different approximations there. So yeah, my limits, and if I wrote this down in my calculator, normal CDF, negative infinity to 95, 103, 5.4, I need to label all 4 of those. It's also a great idea to draw the picture. If you draw the picture, you're kind of telling them you know what the mean, standard deviation, and limits are. But I like labeling the calculator speak as well. I bet the difference in the decimal is because this might be calculated from 86.8 to 95, not negative infinity to 95. But either way, the answer works out the same way. Okay. All right. So yeah, normal curve, that shows up a lot. Random variables, it is either going to be continuous or discrete. A continuous random variable is probably something that's going to follow like a normal curve, a density curve of some to some extent. A discrete random variable might follow a custom distribution, which we'll see some of those later, or it could be a more common distribution shape like binomial or geometric, okay, in which there's conditions that follow for that, which we'll get to in just a second. A discrete random variable is going to have a mean or a standard deviation that you can get using the expected value formula. Basically, you take the value of the variable times the probability of it and do that for each value and add them all up. And then if you're trying to find the mean or standard deviation for something that's binomial or geometric, you can refer to the formula sheet in which that is on there. Okay. The expected value can be found by multiplying the probability of each outcome by that outcome and then summing those up, which that formula is on the reference page as well. It just looks kind of cumbersome. It's easier just to know how you would find it. Okie dokie. So if this were our random variable, so you can see you have the first outcome is 10. The second outcome is 0.25, or the probability of 10. So let's say this is a game and you have a 25% chance of winning $10, a 17.3% chance of winning $8, and then a 57.7% chance of losing $6. What is the expected value you would win? All right, so what you would do, so yeah, here we go. So a game is played below with a deck of cards in which you win $10 if a heart is drawn, that's 25%. $8 if a face card is drawn, that's not a heart, so 17.3, that's the non-face cards that are not hearts. And then you lose 6 for anything else. In a table like this, the probabilities all have to add up to 1. Sometimes they'll give you a blank probability table and you have to fill in a gap by subtracting from 1. Okay. So filling it in, be able to fill that in. If you were given 2 of them, be able to find the third one by subtracting them all from 1. Another common question that I think they would ask is to define the random variable x. In this particular problem, x is the number of dollars won by the player in this particular game. Okay. You have to assign some sort of quantity to your random variable x. So tell the reader what exactly that is. X is the number of blah, 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 whatever. And then to find the expected value of x, here's what that formula would look like. 10 times 0.42 times 25, I'm sorry. 8 times 0.173 -6 times 0.577, or no, -6 because it's a negative. And then that gives you 42.2 cents. All right, so you would expect to win about 42.2 cents the more times you do this over and over and over again, which is a game you should play. You would win more times than you would lose. You would come out on top. If you played this 100 times, you would win about $422. The more times you play a game, the more it's going to hone in on that true expected value. And since the expected value is positive, you would come out on top. Okay. So then let's say the next question is, what are the odds of winning something? Okay. You would take the two positive probabilities and add those up. Sometimes they ask you to take a probability distribution like that chart and add up more than one thing. So in this case, what's the probability of winning? All right, well, you add up the 25% and the 17.3% chance, and you get 42.3. So the odds of winning, you're actually more likely to lose than win, but the amount you win is greater than the amount you lose in a way that you would be able to come out on top. All right, and then E really kind of leads into that next section. If someone were to play this game 10 times, what are the odds that you would win at least 7 times? What are the odds you would win at least 7 times? This turns into a binomial distribution problem. And there are 4 conditions for this particular random variable that makes it binomial. It is binary. Either you win or you don't. So it is binary. There are independent trials. You are not more likely to win the second trial, than you were the first one, assuming you put the card back in the deck. There is a fixed number of trials. So we said we're doing it exactly 10 times. And then all trials are equally likely. You're more likely to win each time, and that kind of ties in with that independent as well. So that would be a binomial question. Now, here are some binomial distributions that you can see on your screen. The first one is a binomial distribution in which the chance of winning was 50% and the trials was 40. All right, well, if there's a 50% chance of winning and there's 40 trials, we would expect there to be about 20. So notice that's the middle of our curve. And the binomial distribution pretty much becomes normal as you increase your sample size. The probability of winning is 70% with trial of 40. Notice it shifts that mean over to the right because 0.7 times 40 is higher, okay? It's 28. You would expect to win 28 times. And then 90 and 40, of course, it increases it over to the right as well. The best way to calculate probabilities on binomial is to use your calculator. If you are looking for an exact number of successes, you would use your binomial PDF. And it's the same menu that we went to a minute ago for normal CDF. We never use normal PDF. We do use binomial PDF if you're looking for the probability of exactly so many successes. And if you want to do less than or equal to a certain number of successes, you would use binomial CDF. It is always going to be inclusive. Okay, your binomial CDF on the TI-84 is always going to include whatever value you put for your endpoint. So if you're looking for, at least 4 successes, then you want to do 3 or less and then find the complement of that by subtracting from 1. Just like with anything, hashtag label your calculator speak. Label it, label it, label it. Tell me what that is going to be. Okay, so here is our problem here. I'm going to pull my calculator back in so we can go through this. If someone were to play the game 10 times, what are the odds they would win at least 7 times? So they could win 7, they could win 8, they could win 9, they could win 10. Any of those options added up. This is binomial because fixed number of trials, 10. It is binary, I either win or lose. They're independent of each other. We're assuming we're putting the card back in, and all trials are equally likely to win. So I'm going to do a binomial CDF. All right, now remember binomial CDF, we have 10 trials. My probability of winning was 0.43, give or take. I can't remember the exact decimal, but that's close enough. And X, it is going to take whatever I put for X and go to the left. Now, I want at least 7. So I want to add up 7, 8, 9, and 10. But I can't go to the right. I can't sum up to the right in the TI-84. And the TI-Nspire, you can. So I'm going to select 6 as my X value. And it's going to add up 6, 5, 4, 3, 2, 1, and 0. All right, so the odds of winning either 0 through 6 times out of 10 is this. So then if I need to find 7 or more, all of them, because it is a probability distribution, is going to be 100%. So 1 minus that, and I get 0.0805. Okay, so think about it like a curve. Okay, and then here I'll label my calculator speak to get that answer. Okay, slightly different because of the 4.2, 4.3. I was 1% off and trying to remember that. Let's see. If I change that, I bet it'll be correct. 4, 2, 3, comma 6 minus. There we go. Yeah, so 0.0739. All right, so again, this was at least 7 times. I had to add up 7, 8, 9, and 10. My calculator will only add up going to the left, so I need to do 6 and then find the complement of that. All right, so if someone came to you and they said that they played this game and they won 7 times, would you have reason to doubt their claim? With a 7.3% chance of something happening, that is some moderate evidence to kind of doubt their claim. However, it is not lower than 0.05, kind of leading into inference here. A lot of times they want you to take a probability calculated from a two-way table or from a binomial distribution and then treat it like a p-value you would do in inference. So 0.073 is not less than 0.05. So we don't really have reason to doubt that they won the game 7 or more times. Okay, not quite there. Don't really have reason to doubt them because the probability of it happening is not extremely low. It is kind of low, kind of questioning a little bit, but not totally calling them out there. Okay, so again, that question's kind of worded like a p-value would be, and they want you to use part E as that p-value. All right, so the only difference between binomial and geometric, which is another type of distribution, is that a geometric distribution does not have a fixed number of trials. However, we're going to play the game until we win. Okay, we're going to keep going until we get a success. Same rules for calculator calculations. It's going to work out the same way. So let's hop on over to Mentimeter. I see that a lot of you have already answered number 1 because I had it there waiting. Okay. So in a certain region, you can hop over to your other device and go to this slide. Remember, if you click the question image, it makes it a little bit bigger, and that also gives you the option to zoom in. So it tells you it's binomial, and the mean is 2.7. And it wants to know, what is the following is the best interpretation of the mean? Now I'll give you a few minutes, and then we will see what we got there. All right, let's do 30 more seconds. And we will see what answers we have. Let's see where we are. For all groups of 45 people, the average number of people without the characteristic is 2.7. All right, so let's look at our answer choices and make sure. Yes, so notice this one right here, okay? And I'm trying to get us back on track time-wise here, kind of rush through geometric. So it tells us it follows a binomial distribution. This option 4, which was the second place answer, 2.7 people are selected until finding someone with the characteristic. That is a geometric distribution because you're doing it until you find somebody. Same thing with the next one is until you find somebody without the characteristic. Okay, so those two are geometric. And I kind of threw you a curveball because we did geometric real quick in the slides and then hopped over here. But this is the correct one. Your mean of your binomial means that for all groups of 45, the average number that you would have that is 45 or 2.7. The expected number of people out of 45 is 2.7. All right, let's move on to the next multiple choice. Go to your device for Mentimeter. What is the probability that it takes 3 rolls until a player rolling dice doubles? So you're rolling 2 dice. I think I cut out some of the text to make it fit better. You're rolling 2 dice. What is the probability that it takes rolling the 2 dice 3 times until you get doubles? 1, 1, 2, and 2, 3, and 3, 4, and 4. And notice this one, you don't actually calculate the probability. You just are looking at the formula, which is on the formula sheet, but you maybe don't need it. All right, let's we'll change it to 10 seconds. I'll tell you what, let's just see what we got. Oh, I already said for 10. All right, let's see where we're at here on this one. Whew, this one was a tough one. I'm not going to lie. It was a tough multiple choice. And looks like the majority of us are correct. Now, a few things to think about looking back at the answer. So if you're rolling doubles, there are 6 ways to roll a double with 2 dice. Both 1s, both 2s, both 3s, both 4s, 5s, and 6s. There are 36 total possible outcomes. Okay, so 6 out of 36, which is 1/6. There's a 1 in 6 chance that you roll doubles. If that is happening on the 3rd trial, that means that the first 2 times you didn't get doubles, which there's a 5 in 6 chance of that. You either get doubles or you don't. All right, so that is why D is the correct answer. You have 5/6 happening the first 2 times, and then 1/6 happening the 3rd time, and then that's what you're doing the game until you get that. So then therefore you get it. Okay. So the answer was D, but that one was tough. Okay. E is kind of flip-flopped. All right. Remember, you're getting 2 failures and 1 success. So you should have 5/6 twice and then 1/6 once, because it's a geometric probability. You're playing the game until you get doubles. Okay. Let's see. What is the expected value of B? Calculator is going to come in handy here. The number of books, 0 books is 35% of people. One book purchased is 20% of people. 2 books purchased, 15, etc. What would you expect people to purchase? How many books would you expect every person to purchase? I am going to do 1 minute on this one. I had to reboot there a little bit. About 10 more seconds. And let's see what we have here. Yay! C was the correct answer. And I put it in my calculator already while you were working it out. This is what it would look like. Okay, so 0, I can make it a little bit larger. 0 times 0.35 plus 1 times 0.2 plus 3, or plus 2 times 0.15 plus 3 times 0.10, etc., all the way through the probability distribution. And that gives me my correct answer. All right, let's look at the next multiple choice we have. One student will be selected at random. Let A be the event that the selected student is a student athlete, and let B be the event that the student drives to school. If the probability of A and B is 8%, 0.08, and the probability that B given A is 0.25, what is the probability that the selected student will be a student athlete? The formula sheet is going to come in handy here a lot. Anytime you just have an event that's classified as A and B and you're given this kind of notation, there are some formulas on the formula sheet that will come in handy greatly. I'm going to pull that up while you're looking at it on your own, and I can walk you through that. Speaking of which, the formula sheet for 2020, even though it was a different exam, is the same formula sheet you will be given tomorrow. They changed from 2019 to 2020 for the new CED. So the formula sheet was not affected by the COVID testing last year. Not COVID testing, but you know what I mean. All right, so here is the formula sheet, and what I'm talking about here. Okay, this formula right here is going to come in handy. Now, it's kind of weird for us because we're given B given A, and the formula gives us A given B. Just reverse them, okay? B given A, change this to event A, and then A and B doesn't matter, okay? So if I'm plugging this into my calculator, I can show you how this would work out here. Okay. I think I'm stacking stuff up over here on my alternate monitor. All right, so the probability of, we're swapping A and B from the formula. B divided by probability of A. So notice that the second number, or the second event matches the denominator. The A and B doesn't matter. A and B is the same as B and A. You could write it that way, okay? And then from our problem, we are given the probability of B given A is 0.25. Probability of A and B is 0.08. And we are looking for that. Cross multiply, 0.25x equals 0.08. Divide by 0.25. And we get our answer, which is 0.32, I believe. Just did it in my calculator. Yep. 0.32, which is answer C. Okay. So that formula was given on the formula sheet, and it made things pretty easy for us to work out. Anytime you see like event A and B, all right, just kind of generalized, or even in this case, it had context, look at those formula sheet answers and see if you can use those. Also remember that the probability of A and B, you can use the multiplication rule to solve that. So the probability of A times the probability of B will give you the and probability if A and B are independent. If they're not independent, you cannot use that. And sometimes the correct answer is we don't know because A and B are not independent. So just be aware of that. Okie dokie. So let's see where we, yep, most people said C on that one. Okay, one more multiple choice. And this is with combining random variables, okay? Which is something we, kind of leads into sampling distributions a little bit when you have two variables and you are combining two things, okay? So I will let you guys look at this one. Use process of elimination. That's probably the most important thing. Not where I want to go yet. Probably the most important thing in AP stats is to use, and the free response or the multiple choice is to use process of elimination. Super, super important there. Okay. So I'll give you a minute to think on this. I'm actually going to set a timer for 1 minute on this one because it is a little bit more difficult. So let's see where we're at. Loading, got 7 seconds left. All right, voting is closed. Let's see where we answered at. Most people had B, which is great. That is the correct answer. And this is a tricky question. So you are combining two random variables. We're subtracting them. The means, you're going to do exactly what you would think. One group is 10, one group is 7, and you are subtracting them. 10 minus 7 is 3. Means are normal, nothing weird, nothing crazy going on, okay? So the mean is 3. Mark out D and E. It's not the answer, okay? Process elimination is huge. Now, you probably remember that standard deviation has something kind of weird on it, okay? So means you can subtract. I'm going to pull my iPad back up here. Try to leave my captions on though. Oh no, don't want to do that. Yeah, there we go. All right, so our means, we're going to subtract the mean of R minus the mean of S, which is 10 minus 7, which is 3. Now for the standard deviation of R minus S, I cannot just straight up subtract those. So what I have to do is I have to do the Pythagorean theorem. I can combine variances, but I can't combine standard deviations. Okay? And standard deviations are always added. You're not going to subtract those in this case. So that ends up being the square root of 4 squared plus 3 squared, which is the square root of 16 plus 9, 25, which is 5. All right, so the answer would be B in that case. Now, when you're combining random variables, that is the Pythagorean theorem of AP statistics, when you're combining two standard deviations. Means are normal, you combine them like always. Standard deviations, you have to do that. That is when you are combining two separate random variables like we were in this question. If you are adding a scalar, like just adding a number 2 to everybody, scaling everybody's score up by 2 points, okay? That's going to scale the mean by 2 points, so you would add 2 to the mean. The standard deviation is not affected by adding. If you were to multiply by a scalar, that is going to multiply the mean and standard deviation. So again, if you're talking about if you're adding a scalar, just adding 2 to the whole distribution, then you add to the mean, don't do anything to standard deviation. If you are multiplying a distribution by a scalar, you multiply your mean and standard deviation. If you are combining two totally separate random variables, this is how you would handle it. Okay, and you're never going to multiply a variable times another variable, so you don't have to worry about that. You're just adding them. Okay, let's see, one more, and then we'll, nope, only 4 on that section, which is good. We need to hop back on time here. So the next thing is we are going to do a little brain break with some of your all favorite music artists. All right, one of mine. All right, so there is the QR code. Scan that, enter the class code 13BCF, and you are going to rate how much you like Harry Styles and his music on a scale of 1 to 10. So we'll take a little breather here for a minute, and then we'll hop into Inference.
I don't know if I could ever go without watermelon sugar high, watermelon sugar high, watermelon sugar high, watermelon sugar high, watermelon sugar strawberries on a summer evening. Baby, you're the end of June.
I have also added the link into the Q&A, so maybe you can access the link from there if you can't scan the QR code. So I put it in as a question. You should be able to see it. Okay. Looks like some people may be upvoting it already. All right. Get up, stretch for a minute. answer the question. We'll vibe to some hairstyles for a minute.
Tastes like strawberries on a summer evening, and it sounds just like a song. I want your belly and that summer feeling. I don't know if I could ever go without watermelon sugar high, 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 watermelon sugar high. I just wanna taste it. I just wanna taste it. Watermelon sugar high. I just wanna taste it.
So I forgot to enable data collection. So try now on the website with the QR code to enter your rating of hairstyles. My bad on that. Should be able to enter it in now. I'll give you all another few minutes to do that. Okay, I'm seeing some data. Someone voted an 8, so I'll give you all a second to do that. I want to know, how popular is Harry Styles? On a scale of 1 to 10, how much do you like him? Wow, it just went from like 2 people to like 100 people on my screen. That's pretty awesome. You can see the dot plot and that sort of thing too. It's a really awesome website. We've been using a little bit this semester. Somebody is a huge fan there. All right, take about another 2 or 3 minutes on that, and then we will hop over there and get going. Whew, I need to stretch up, stand up and stretch for a minute. I'm sure you all did too. All right, let's see. Let's see. 13B. All right, so hopefully you all got that in there. I'm going to pause the data collection, and we had 302 people answer, which is pretty fantastical. Okay, so let's hop on in now. This is the big part of the exam, and this really kind of flows into our mixed review that we'll get to here shortly, which is inference. Okay, that is the act of using a sample to make a prediction or an investigation about a larger population. Okay, I'm either using a sample to predict what the true population proportion or mean. I don't know what happened there. That was strange. It's like it just poof disappeared. All right. I hope we're back good now. So full screen and captions. Check 1, 2, 3. Check 1, 2, 3. All right, I'm seeing back, the stream is back up, hopefully. That was very bizarre. I don't know what happened on that one. So yeah, so inference is about taking a sample to predict something about a population. Two main types. If you want to actually predict or estimate a population proportion, you're going to use a confidence interval. And if you are wanting to estimate, or if you're wanting to test against some other claim, then you would do a hypothesis test, okay, which are two different things there. I'm trying to get my captions back on. Jeez. All right, maybe now. 1, 2. Hopefully y'all can hear me. Hopefully things are not, I don't know why captions are not wanting to work. All right, yep, looks like we're back, but no captions. Strange, strange, strange. All right, so but before we look at inference, we need to look at just some reminders for our foundation, which is sampling distributions. So remember, if you have a population, this population here is not normal. So all these X's represent individuals in the population. Then if I take a sample of a given size from this population and average those, and I take every possible sample of a given size, say size 40. Generally speaking, the larger my sample size is, all those possible averages will make a normal sampling distribution. So again, a sampling distribution is all possible samples of a given size, and all of those possible samples have an average each sample. All those averages will make a pretty normal distribution, which is huge. That's what opens up the door for being able to test if a sample that we got should happen if a claim about something is true. So in order to construct a sampling distribution, we need 3 conditions. Our samples have to be random. That means that the average of all possible sample means is in fact our population mean. So it is unbiased. Okay. I need to make sure that the samples I'm taking are reflective of the population I'm trying to either judge or I'm trying to predict. So therefore they have to be random. Our population is at least 10 times the sample size. That ensures that when we are sampling without replacement, that means it's not independently sampled. It's such a small difference that we can say that our samples are essentially independent of one another. Okay, our sampling distribution is approximately normal. If it's means or quantitative data, our sample size has to be at least 30. If it is proportions, then the number of successes and the number of failures has to be at least 10. So NP greater than or equal to 10, N1 minus P greater than or equal to 10. So the expected number of successes and the expected number of failures is at least 10. So when finding a probability using sampling distribution, it is going to work exactly like normal CDF. The only difference is that the standard deviation is going to change. The larger our sample size, the smaller our standard deviation. Okay, the more we focus in on the larger our sample size, the more we're going to hone in on our population mean or our population proportion. All right, so once we have that, we can then build a confidence interval. Okay, the first form of inference that we'll look at is building a confidence interval, which is used to estimate the true proportion or the true mean of our population. That is a form of inference where we use a sample and use it to predict our population. Okay, and this, you kind of see an example here. So our sample is in the middle of our confidence interval, and then we add and subtract what we call a margin of error. And that margin of error gives us some buffer zone to determine where we think our sampling or our population proportion is or is not. So here's the two basic formulas, okay? If we are doing proportions, this is the formula for a sampling distribution. We take our sample proportion plus or minus our z-score times our standard error, which is found with this formula. It is on your formula sheet, okay? So I can find that right there. Okay, our formula sheet right here. Okay, it tells you the confidence interval is the statistic plus or minus the critical value times the standard error. Here is your statistic, 1 proportion, 2 proportion, 1 mean, 2 mean, or 2 sample. And then you know it's a z-score for your critical value for proportions, a t-score for means, and then here's your formula for standard error. 1 sample, 2, or 1 proportion, 2 proportion, 1 sample, 2 sample. Okay. Now sometimes on multiple choice it will be a 2 sample, and they will have worked it out so it doesn't look like this. It actually looks more like the top one, but it's still the correct answer because they have done a little bit of simplifying. Just be careful of that. But a lot of times you can just pick out which one it is based off of, you know, whatever. But these are for 1 sample. These are your proportion and means confidence interval formula. All right, any type of inference, the steps we typically go through. State. All right, so for confidence intervals, tell me what are you trying to estimate? I'm trying to estimate the true mean or true proportion or true difference in means and proportions of blank, whatever it is, the context of the problem. Again, context is super, super important there. Plan. We have to check our 3 conditions for inference. If it's an experiment, make sure you don't just note random sample, but you note random assignment, okay? And no independence for experiments. So that's kind of the catch. If it's an experimental study, and you can see that because treatments were randomly assigned, you need to note in your plan section that treatments were randomly assigned, not just the random sample part. And then you do not check the independent sample, all right? If it is a 2 sample, you need to check the normal condition for each sample. And if it's proportions, you want to pool your proportions together. That is on your formula page as well. You pool proportions, okay? You do not pool means, which in your calculator you would select not pooled. So use your pooled proportions for that normal check. All right, write down which interval you used in the calculator by name and write out the interval. If you chose a 2-prop Z interval, write down 2-prop Z interval and then write out your answer. You do not have to write the formula. You can, but that opens up some room for error that sometimes messes things up. It's better just to write the answer and which one you chose in the calculator. And then conclude. This is your CAN statement for conclusions on confidence intervals. We are 95% confident that the true mean or proportion of whatever is between blank and blank units. Okay, that's your answer. You're explaining your answer in context. The conclusions are really the most important part from inference, both confidence intervals and hypothesis tests. Always, always, always use context. Context, context, context. It is super important, both in the state section and in the conclusion section. Very important. Okay, so a cool little website here, which kind of explains that confidence level. All right, let's see. So let's do means actually instead of proportions. So means, we're going to do a t interval. Let's say our average is 56 with a standard deviation of 3, sample size of 100, and I'm going to take a sample. All right, so this little, oh, let me zoom in, good. This represents my sample. So I have my population that had a mean of 56 and a standard deviation of 3. I took one sample of 100. This is what that sample looks like. I had 145, 146, 147, some in the 50s, some in the high 50s where most of it was at. My average for my one sample was 56.27. That is the black dot on this little line here, 56.27. Then, based off of my sample size, I calculated my standard deviation, and I add and subtract, and I can see that this particular confidence interval does contain my 56, which is my population value. Okay, so I did one interval, and that one interval was accurate. It contained my population mean. So now let's say I do it 100 times. Yeah, there's some of these that are in red are not containing my population proportion. Okay, so right now, about only 94% of them did. Okay, and then if I keep sampling, notice if I keep sampling and sampling and sampling, my running total gets really, really close to 95%. So 95% of my samples I've created at this point, 1,101 unique random samples of 100 from my population, okay? 1,101 out of those, 94.6% crossed 56. They contained 56 within my interval. And that is what, that's what we're meaning by 95%. If I were to repeat this process over and over and over again with unique samples, 95% of my unique random samples would generate confidence intervals with that contain my true population mean. So that's what the 56% represents. Or the 95%, I'm sorry, not 56%. That's what the 95% means, is that if you were to repeat a process over and over and over many, many times, 95% of the resulting confidence intervals, so 95% of the samples, would produce confidence intervals that contain the true mean or proportion. All right, so then hypothesis test, kind of flipping over to that. Sometimes we are given a claim about the population. So we're told that the population is this, population's 56. And then we pull a unique random sample that doesn't really match that claim from the author, from the article, or whatever. And then we want to test, hey, are they right? Because I know that my sample is 52. So is their 56 really right? Or do I just have a really weird sample that doesn't match theirs? Okay, so in order to do that, we're going to run a hypothesis test. If you're asked to estimate, that is a confidence interval. If you are asked to test, does the data show significant evidence? Do the data give convincing evidence? Or is there evidence of this claim being wrong? That's where you would run a hypothesis test. The process is very, very similar, and we make our conclusion based off of a p-value, which is the probability of, this is important interpretation here, the p-value is the probability of obtaining a sample value as extreme as ours, either greater than ours or less than ours, or maybe just not as equal to the mean as ours, if we assume our null claim about the population. So the p-value, the interpretation of that p-value is assuming the null is true, what are the odds of getting our sample? Okay. And your critical value, basically you take your sampling distribution and then you match it onto either the Z curve or T curve. Z for proportions, T for means. That's an important distinction to make as well. And you calculate its critical value, observed minus expected divided by standard deviation, that same Z-score formula you learn about in Unit 1. And then you put that on the standard normal curve or the standard T curve, and the calculator does a normal CDF or a T-CDF for you and finds the probability of getting that value or more. And then you can see how rare that was. All right, so the tweaks here. In the state section, and we're going to go over some examples of this very soon, you want to make sure your hypotheses are there and tell me what those parameters mean. So your null hypothesis is always dull. It's always that there's not really anything going on different from the author's claim. Okay, the mu equals 3.5 because that's what the author said. And then your alternate hypothesis is that it's different than 3.5, which is what your sample leads you to believe. So your null hypothesis is always an equal sign, and it's always using the population parameter, either mu or p. Do not use x bar or p hat in your hypotheses, but your mu is always equal. It's equal to the amount given in the claim. All right. So p or mu equals whatever. That might be that the two things, you know, if you're looking at two proportions, it's that the P1 is equal to P2. But you have to clarify what P1 and P2 mean. P1 equals the true proportion of people from group A who like Takis. And then P2 is the true proportion of people from group B who like Takis. The null is dull. It's that those two proportions are equal. There's no impact on the love of Takis based off of which group they're in. And then your alternate is what you're thinking based off your sample. Hey, my samples are actually different than what this article claims, so I'm going to test that. Okay, so my P or my mu is greater than, less than, or not equal to that. Never use P hat, never use X bar. Same thing for conditions, same conditions. Experiment, random assignment, and no independence. If it's two sample, you have to check the normal for both sample. For random, just quote the problem, which we'll look at some examples in a minute. Write down which test you used in the calculator by name. Write out your test statistic, either your Z, your T, or your chi-squared, which we'll touch on. And then also write out your p-value that the calculator gives you. And then if you're doing means or chi-squared, write down your degrees of freedom. And then your conclude. Okay, those are your two options for conclusion. Since p is less than 0.05, we reject the null. We have convincing evidence that the blah, blah, blah. Or since p is greater than 0.05, we fail to reject the null. We do not have convincing evidence that the blah, 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 blah. Okay, so those are the two conclusions for hypothesis test. You are comparing your p-value to an alpha value. Typically, alpha is 0.05. They could throw you a curveball and give you a 0.10. In that case, you're just going to compare your p-value to 0.10 or maybe 0.01 or 0.02. If it doesn't specify an alpha, you're going to use 0.05. The p is low, you reject the hoe. P is not low, you fail to reject the hoe. You never accept either one. I like to say you side with one or the other, but you do not just accept them. Avoid the word accept in either of those. So your first sentence in your conclusion is, what decision did you make about the null? Did you reject the null or did you fail to reject the null? And then your second sentence is, therefore, what do you believe about the alternate? So if you reject the null, that means you're siding with the alternate, which means you have evidence of the alternate hypothesis. If you fail to reject, then you are siding with the null. Therefore, you do not have evidence of the alternate hypothesis. Okay, and again, always, always, always use context. That's why, I put here context of the alternate hypothesis. All right, and this is the big question, and this next little probably 4-minute span here is probably the most asked question for people. Which inference method do I use? All right, first thing, is it a confidence interval or a significance test? If it asks you to estimate something, it's going to be a confidence interval. If it says to create and interpret a 95% confidence interval, clearly it's a confidence interval. Okay, confidence intervals usually cue you to do a confidence interval, or they say to estimate the true proportion or true mean. Confidence intervals are used for estimation. Significance tests are those keywords. Do the data give convincing evidence? Can you find convincing evidence that blah, blah, blah? Okay. All right, so once you determine that, is it means or proportions? If it is means, you're going to do either a t-interval or a t-test. If it is proportions, you are going to do a z-interval or z-test. And then you have that kind of sidebar of the chi-squared, in which it is a two-way table or a multi-variable or multi-category variable. But if it's just, one or the other, yes or no, then it's just going to be a z-test or interval. Okay, but if you have a confidence interval with a two-way table or a multi-categorical variable, then you would use chi-squared, which we'll touch on that once we get there. So again, is it proportions? Is it chi-squared? The next thing, is it one or two sample? Okay, if it's one sample, you're going to do either t-test or t-interval. If you're doing proportions, you never select z-test or z-interval from the calculator. You have to select the one for proportions. One prop z-test and one prop z-interval. Anything with proportions, you're going to have that prop in front of it. All right, and if it's one sample with a chi-squared, if it's a one-way table, it's going to be goodness of fit. If it's a two-way table with one sample, it's association. All right, two sample with z or t, that's two sample t test interval or two prop z interval test. Okay, so all the z's are going to have prop in front of them. The t's do not. They might have two sample. If it has two clear samples and it's a two-way table, you're going to do chi-squared test for homogeneity. All right, let's look at some practice questions. Let's hop on over to Mentimeter. Okay, y'all answered a lot of questions here. Technical difficulties kind of had to slow things up. Y'all have some great words here from our little word wall. I really love that. I wish we would have had more time to really look through that. Confidence intervals, panic phantoms. Some people do panic instead of SPDC. Population versus sample. We are 95% confident that the ... prediction, z-test, all those are great things. So let's look at our first question. And this is one where you are just clarifying which test you would use for the study. Let's see what you all got on this one. Few more seconds to answer this one. All right, let's see where we are at on this one. I don't know why it's not wanting to give me our responses. I can see that most of you have all answered. All right, so this is dealing with means, clearly. And we have 35 cartons from each store, and we are comparing them between store A and B. And it says the difference in the mean carton price will be calculated. What is the following is an appropriate test for this study? So weird that it's not giving me y'all's answers. So it's dealing with means. So proportions is out. Okay, A is out. A one sample t-test. We don't have one sample. We have two samples. We have two grocery stores here. Okay, out. Match pairs sounds kind of close. And two sample sounds kind of close. And then a two sample z-test for population. Again, we're talking about proportions. That one's out. So C and D is what I would narrow them down to be just immediately. Okay. Now, the difference here is that we have two samples. A match pairs t-test is only going to have one sample from that receive both treatments. Okay. And you can't really have one group of eggs sold here and sold at A and B. So the answer here would be a two sample t-test for the difference between population means. So we have a sample of 35 at group A and a sample of 35 at group B, and you're comparing those averages. Okay, the average from store A and the average from store B. So there's a sample A and a sample B, two samples. A match pairs t-test is only going to have one sample in which, you know, each carton of eggs was sold at both stores, which wouldn't really make sense, like I said. So let's look at the next one. Oh, that's the same question. I forgot to change it. All right, so here is number 3, actually the second one for us there. To test the effectiveness of an exercise program in reducing blood pressure, 15 participants had their blood pressure recorded before beginning the program and after completing the program. The difference before and after was recorded for each participant, and the sample mean difference was calculated. A hypothesis test will be conducted to investigate whether there is convincing statistical evidence for the reduction in blood pressure for all who complete the program. So again, think about process of elimination here, because that is going to be very important. Does the people completing the program have a reduction in blood pressure? All right, looks like most people have had a chance to vote. We're not going to get responses this time. Yes, I did. And it looks like E is the leading response. All right, so let's go step by step because this process of elimination is huge here. Your hypotheses should never have X bars. A and B are out, okay? Now, C, D, and E all look good. They all have mu. They're referring to the population parameter. They all have equals in the null. It's just, is this question asking about, is it not equal to, or is it greater than or less than? We're clearly looking at there is a reduction in blood pressure. So that means the after would be less than the before. Okay, it tells you after minus before. So that means after is lower, minus before, that number would be negative, so it would be less than 0. Greater than 0 means that it would go up. We want blood pressure to come down. That's kind of tricky. You got to be very cautious there and figuring out which one it is. It does specify that it is a one-way test. Now, this is a matched pairs test, by the way. So the last one we did was not. This one is. We have one sample of 15, and every person is receiving the program. They're receiving the treatment before and after the program. So they're getting both treatments, which is blood pressure before and blood pressure after, and then they're comparing those. This is a matched pairs t-test. There's one sample, so you would put it in your calculator as a one sample t-test or just t-tests. All right, but then the answer is going to be E because after minus before, and we want to see if it brings it down, reduces it. That would make the after minus before negative. All right, next one gives you a p-value of 0.026. What is the interpretation of that p-value? Cool. Hey, I'm back in camera. Awesome. Cool, cool, cool. All right. Just feel like I need to be able to, I mean, I'm not seeing you all, but I feel like I need to be interacting more. All right. So our p-value is 0.026. Now, it's asking for an interpretation of the p-value, not the conclusion off of the p-value. And those are different. Okay. So the p-value, we have to assume that the null is true. That's the big thing here. All right. And it says the university reports that they spend an average of $100 on the first date. And then the sociologist gets a sample and gets 92.23 out of a sample of 32. All right. So the correct answer you should have here is D. All right. Notice in D, if the mean amount of money that students from the university spend on a first date is $100, the probability is 0.026 that a randomly selected group of 32 would have a mean of that or less on their most recent first dates. Okay, so we're assuming that the mean is actually 100. That's the important part. E, you're assuming the null. You're assuming that it's less than 100. Remember, your null is always equal to, and that's what's given in the magazine article. A, B, and C don't have anything about assuming the null, and that's what you should look for when you're interpreting a p-value. Good job, good job. All right, free response time. Whoop, whoop, whoop. I'm more excited about this than you all are. So I want you to, as best you can, do this in Mentimeter. I don't know if I'm going to look at everybody's responses because I'm actually going to work through it with you. But a sheet of paper, I would say sheet of paper is probably best. Okay, so work this out through a sheet of paper and see how we do. All right, here's that key statement. Can one conclude that the mean manual dexterity for people who have completed the 6-week training program has significantly increased? Support your conclusion with appropriate statistical evidence. That sounds like an SPDC problem. Okay, so I'm going to set a timer for, let's go 12 minutes. Actually, I don't want to fall too far behind. Let's go 9 minutes, and then we'll go over it. So if you don't finish it, that's fine. You might not finish it in the 9 minutes. No big deal. Again, I would do it on a sheet of paper. It's going to be really hard to do it all in Mentimeter typing. Fortunately, we don't have to worry about typing out free responses. So 9 minutes starting now. If you need to see the picture a little bit better, you remember on Mentimeter on your phone or whatever other device you're using, you can click on the picture and then zoom in from there. Okay, calculator is also going to come in handy. I'll work it through on the calculator for you as well. About a minute and a half left. Muted. There we go. Sorry, I was muted, everybody. So that is our state. So we can see that this, I'll say it again since I was muted. We can see that it is two sample and not two sample, one sample, but two numbers, one for each sample. Okay. So that's why it's a matched pairs t-test. Our null is that it's always equal to 0. And then I want to say what mu of d represents, the true mean difference in dexterity levels after program. So we're saying that that difference is going to be greater than 0 after the program, and hence increase their likelihood. Okay, so that's kind of my start there. Again, my null is dull, and then my alternate is that something's going on. Hey, it's increasing something. And then I got to tell me what mu of d represents. Okay, got to clarify what my parameters is. I went ahead and wrote what test it was. That kind of sets me up, okay, for how I'm going to continue. And then we have to plan. All right, so I have to check random. And it does tell me a random sample of 30, or 15, I mean. And I'm just going to quote the problem. Random sample of 12, actually. I'm sorry, 12 people. So I'm going to quote the problem. Good there. Independent. It is reasonable to believe that 120 people participate in program. All right, it's totally reasonable to believe that they could get 120 people to do it. So basically what I did is I took my sample and multiplied it by 10. And then normal, central limit theorem is not met here. All right, it doesn't tell me it's normally distributed, and 12 is not greater than 30. So what I have to do, and I've already done this in my calculator kind of ahead of time. All right, so I made my list 1 before, list 2 after, and then list 3 I set to be equal to L2 minus L1. And I'm going to create a box plot of L3. And I want to do a modified box plot because I have to check to make sure there's no outliers. It's L3. And then I'm going to zoom stat, and it automatically zooms in for me. All right, it's pretty skewed. All right, I'm going to sketch it out. But there's no outliers. Okay, so I'm going to continue on under normal because my box plot does not show outliers. Okay, and I'm going to sketch out that box plot. All right, that's my sample data. And by skewed, really, we're just looking for outliers. I would say this is skewed to the right because, you know, you got that kind of long tail there, but still not like super skewed because of outliers. So we'll continue on. All right, so then we're going to do the test. So in my calculator, I'm going to do stat test. This is a 1 sample t-test. Match pairs is only 1 sample. And I'm going to run it off my data, which in this case is my L3, because I'm looking at the differences. And I'm checking to see that it is greater than 0. And you can either do calculate or draw. I'm going to do calculate. And I get my t-score is 3.538. My p-value is 0.002. And since it was a t-test, I need to include my degrees of freedom, which was 11. So that's what my do section looks like. I have my critical value from my calculator. I have my p-value from my calculator, and then my degrees of freedom if it's a t-test of any sort. All right, last thing is to conclude our p-value is low. So since 0.002 is less than 0.05, we reject the null. Okay. P was low, we dropped the hoe. That means that, so this means we're siding with the alternate. So that means there is convincing evidence of that alternate hypothesis. So that means that dexterity levels do in fact increase from the program. All right, that would be a complete response. Everything's there. I checked my conditions. I named the right test. I stated my hypotheses correctly, and I did the calculations, and I concluded. Okay, so we are there. We're good. Let's see. A little note here, just to try to maximize your credit. If you get one of these and you're really stuck on what to do, make up a p-value and do a conclusion based off of your made-up p-value. All right, you can, if you get a wrong p-value and then conclude correctly based off of that, you can still get credit for the conclusion, which gets you like at a 1, okay, which is, you know, we don't want to get 1s on free responses, but it's better than a 0, okay? So that is how you would do that free response there. Okay. All right, let's kind of giving things away here. We are going to use that Harry Styles data in just a minute. But let's go. Now we're going to kind of mix review things and look at things from the whole course, multiple choice wise. Okay, so all Mentimeter, here is our first multiple choice. We'll try to get, we won't get all 15 in. You can go through the deck and look at them later if you'd like. We'll kind of skip to some that are important that I feel like we maybe haven't talked about. And we'll wrap things up here in about 35 minutes. Okay. The best interpretation of this standard score. So her z-score is 1.5. Let's see. B, almost everybody said B. That's fantastic. We talked about this earlier. The 1.5 standard deviations above the average systolic blood pressure. Above because it was a positive value. Okay, great job. Great job, everybody. Let's see what number 2 is. Okay, little value here on hypothesis test. So let's take a look at that one. All right, let's see how we would conclude. Most people said A. Let's see. There's reason to conclude that mu is greater than 10. Our p-value is low, so we would reject the null. So yes, that would be accurate on A. Good job, good job. All right, let's see number 3. Oh, this is a great one. Chi-squared, chi-squared. Super important here. We haven't talked on this very much, so let's definitely look at this. Common type of chi-squared question to be asked too. All right, a few more minutes on this one. This one's tough. Like I said, we haven't talked about this any, but we will discuss kind of how to eliminate some answer choices here and go through how to solve this one. All right, let's see where we're at. Kind of expect this to be. Oh, look at that beautifully skewed left distribution there. All right, yes, we have a huge array there of values. Okay, I think E is the correct answer. We'll go through it and see. All right, now when you're doing chi-squared, it is observed minus expected squared divided by expected. So the second two numbers should match in all of them. All right, looking at B, we have 35 and 50. Those don't match, so B is out. The last number in the first fraction does not match the denominator. The other ones look good on that account. So the next, let's look at degrees of freedom. The degrees of freedom for a two-way chi-squared test like this is the number of rows minus 1 times the number of columns minus 1. And we don't include the totals. So we have 2 columns, 2 minus 1 is 1. We have 2 rows, 2 minus 1 is 1. So the degrees of freedom is 1 times 1, which is 1. So that leaves us with either D or E. All right. So we need to make sure we start off with observed, which is 50. Then we start off at 30 and then 20 and 60. 50, 30. Or or 50, 20, 30, and 60. It looks like they all start off with the right number. So then we got to find out the expected counts. 2 ways that you can do that from your calculator. All right, if you want to, you can put in a matrix. All right, I want to edit matrix B or matrix A. And I want to make it 2 by 2. Again, we leave out our columns. And I'm going to enter in my matrix 50, 20, 30, and 60. 50, enter. 20, enter. 30, enter, and 60. And then I want to run, I'm actually going to run the test, okay, even though we just need the chi-squared value. But if I run the test, it will give me a matrix B, which is my expected counts. See how it says it's going to store it in matrix B. So degrees of freedom is 1. It also tells you that. And then I'm going to look at matrix B. So my observed is 35, 35, 45, 45. So over here, I need to pick the one that's going to be 50 minus 35, which is answer choice E. And then 20, observed minus expected minus 35. The other way of doing it by hand, to find the expected counts, you take the total row times the total column, so 70 times 80, and then divide it by the total. That will also give you the expected counts for each row. 70 times 80 divided by 160. 70 times 80 divided by 160. That's why they're both 35. 90 times 80 divided by 160. And then 90 times 80 divided by 160. They're both 45. Okay. The calculator is what really comes in handy there on that. All right, let's see. We might skip to some free responses now. I want to see if there's anything we didn't cover. All right, this is that margin of error based off of the confidence interval formula. It's a 95% confidence interval. The sample size is 9. That means degrees of freedom is, or sample size is 10. Degrees of freedom is 9. Okay, so for my formula sheet, remember we talked about this in one of the other streams. You can look at the t-score. It's means, so it's t-score. And my degrees of freedom is 9. And I'm going to scroll over to a confidence level of 95% at the bottom, which is 2.262. So I need to pick the one with 2.262. It would be E. All right, that's the only one that has the correct critical value for degrees of freedom of 9 with a 95% confidence interval. Okay, just real quick there on that one. All right, another concluding a confidence interval. Now this one too, one thing we didn't talk about is type 1 and 2 errors. The probability of, so a type 1 error is when you reject the null incorrectly. And a type 2 error is when you fail to reject the null incorrectly. All right. And the probability of a type 1 error is your significance level, 0.05 typically. And the probability of making a type 2 error is 1 minus the power. Okay. The most common thing you're going to see with type 1 error is to pick which error happened. So like if you rejected the null, you could have made a type 1 error, which means you rejected the null and you shouldn't have. The null was actually the true one you should have sided with. And then specifying a consequence of that as well is also important. Okay, so just wanted to touch on that. We've got plenty more resources you could go back and look at on that. We'll also be in the Discord discussing that. I'll tell you what, let's go on to free response. I'm going to hop on over there. We're going to hop off Mentimeter and look at free response. It's our first one, which we need to have our data. We need to reload it. Because I have our class data based off of our Harry Styles. Loading, loading, loading. Keep those pages loading. Let's close some of this stuff out. All right, we are coming along, coming along. Sorry, it is taking so long to load. Why is it taking so long to load? Oh my goodness. I swear I have like my own Wi-Fi network just for this stream. Like, I mean, I have two Wi-Fi networks and I've had to swap them once. Maybe I just live out in the country. All right. Well, let's see. There it is. All right, present. Presenter view. All right, so according to a recent nationwide survey, teens rate their love of Harry Styles on a scale of 1 to 10 with an average of 8.2 with a standard deviation of 0.3. Based on our sample of 286 earlier, we have the following statistics. Does the data give convincing evidence that teens rate their love of Harry Styles lower than that average of 8.2? So I'm going to give you all about 8 minutes to go through this. There's that cue, all right, of SPDC. It is a hypothesis test. So I will give you all a few minutes to work on that, and then we'll go over it. Also, part B, what type of error is possible? You'll have to have your conclusion from A in order to answer that. And what would be a possible consequence for his marketing team from this error? All right, we're going to do 5 minutes. I know you might not finish, but I do want to give us a chance to go over it. So I'll give you 5 minutes, and we will go over it pretty quickly to hopefully we can get through at least 1, maybe 2 more free responses. All right, I'm going to cut us off at about 1 minute on the timer, just to be sure we're able to finish this and go over it, and then also look at the another one. All right, so let's see where we're at here on this. I'm going to share my iPad screen. I've already got a lot of it worked out, except for the test part. So our null hypothesis is that it's equal to what the article said. And then our testing, if it's less than that, I want to clarify that mu is the true mean Harry Styles rating for teenagers. Random sample, we kind of assumed it's a random sample of 286. Clearly, we're all in AP stats. So that's not really random, but probably not biased in a way that matters. And it is reasonable to believe there's more than 2,860 teenagers. Normal central limit theorem applies because 286 is greater than 30. And then I'm going to refer to my calculator for the rest, for my actual calculations. So stat. This is a test. This is a one sample t-test. All right. I am testing against 8.3. That's my null value. My mean is 6.43. Whoops. So my mean is 6.43. My standard deviation was 2.991. And a lot of people who love Harry Styles and some not so much. 286. And I'm testing if it is less than, because our sample is less than what they said. So we want to see. And then calculate. Oof. Oof. Somebody be lying. All right. So that's our values we need. And then we would write that there in our do section. And then our conclude, since 0 is less than 0.05 or whatever significance level we were given, we are going to reject the null. There is convincing evidence that the true mean rating for Harry Styles is less than 8.3, which makes me very sad because I like Harry Styles. He's got a good music there, good pop music. I'm not a huge pop music person, but I do like his music. All right, so B is what type of error could we make and what is a consequence of that error? All right, our decision was to reject the null. That means that it is possible we made a type 1 error. Type 1 has one answer in the decision. Type 2 has failed to reject in the decision. Type 1 error, we rejected the mean rating of 8.3 when it is actually 8.3. So a consequence for Harry Styles' marketing team is that they contribute a lot of money to marketing to gain more fans when the money would be better spent on merch for the existing fans. All right, so my decision here makes Harry Styles' marketing team say, oh crap, we need more fans. We got to get people listening to our music more. So they're going to spend more money marketing his music to make fans. Whereas in reality, if I made that error, the true mean rating is actually about 8.3, and therefore that money would be better spent on merch for the existing fans so they can make more money that way. Okay, so the money was wasted on the marketing of creating new fans. It would have been better spent on marketing to the fans that were already there. So that would be a consequence of that error. Okay, I could totally see tomorrow being a question like that, part A and part B. Your grading rubric, component 1, component 2, component 3, component 4. All right, and you could, like I said, you could make up a p-value if you totally get lost. Make up a p-value. You probably could name the test too. Make up a p-value, conclude accordingly, match your error accordingly, and be good. Okay, let's look at one more free response. We're going to do it pretty quickly. We have our burrito question. We've already done one like that. So let's go to this one here. Rocket models are sold by Elon Musk's SpaceX Bandicoots for a cost mean of 150 Dogecoins with a standard deviation of 12 Doge. The cost of rocket models are normally distributed. So they make a whole bunch of rockets and they sell them for whatever price they're worth. And the average cost is 150 Dogecoins, which we know could be anywhere between 75 to almost $100 or all the way down to basically nothing. With a standard deviation of 12 Doge, okay? And it tells us they are normally distributed. So, part A. What is the probability of selecting a rocket at random that costs more than 170 Doge? All right, so we got our normal curve for our rockets, which is a mean of 150. And then we got our normal curve at 170 or above. And I'm going to do normal CDF because it tells us it's normal from 170 to infinity with a mean of 150 and a standard deviation of 12. And I want to label my calculator speak. Lower limit, upper limit, mean, and standard deviation. Okay. And then in my handy dandy calculator, I'm going to go to my distribute menu. Second, distribute, normal CDF, never normal PDF. And we're going to go from 170 all the way up to a jabillion, bagillion, A lot of ways you can put that in there. The mean of 150 and a standard deviation of 12. I'm going to paste that in. I'm going to get my probability, which is about 4%. So that would be part A. All right. Part B. Yep. We'll be there in a minute. To better estimate the true cost, the bandicoots have decided to select a random sample of 50 rockets instead of just one. Describe that sampling distribution. Okay. So describe the sampling distribution. That's the same as describing a distribution, but it's the caveat of being a sampling distribution. So you should think, I'm going to cuss the data. My mean is my population mean, which is 150 Doge. All right. Outliers we actually don't have to do, which we'll get to in the shape. My shape is going to be approximately normal because remember, sampling distributions are approximately normal when it meets either the central limit theorem or the large counts condition. So because 50 is greater than or equal to 30, my shape is approximately normal. You have to include that wiggle word there. And then my spread is going to be my standard deviation of all my samples is going to be 12 divided by the square root of 40, because that's the formula that's given on the formula sheet. Let's see what that is. 12 divided by square root of 40. So my new standard deviation is 1.897. Okay, so that is how you're going to describe a sampling distribution. It's the same as describing a regular distribution. Those problems show up a lot and they throw people for a loop. It's the same. You use your formulas for center and spread, and then shape is that normal condition, which in turn kind of cancels out there's outliers. If it's approximately normal, there is not going to be any outliers. Okay, so that is how I would do part B. Sorry, I forgot I had not shared my my thing. And then I included context because I put Doge there. Okay, I think that's good enough for context. You could say mean cost of a random sample of 50 rockets is 150 Doge, but that'll work. All right, so C. What is the probability of selecting a random sample of 50 rockets? We know it's normal because of the sample size. 170 to infinity with a mean of 150 Doge and a standard deviation now of 1.897. So our standard deviation has gotten smaller because we are not just selecting one. We are in fact selecting 40 Doge. Oh, I said 40. I meant to do 50 there. So that standard deviation is going to be a little bit different. I'll fix that real quick. I know we're going over a few minutes. I apologize, but I definitely wanted to talk about sampling distributions. 1.697. No, 897. All right, and then I'm just going to copy and paste my normal CDF from before and just change my standard deviation. It's going to be different. 0.697, and I can guarantee you it's basically going to be 0. It's approximately 0. I'm going to label my calculator speak again. Mean of my sampling distribution, standard deviation of my sampling distribution. All right, and then the last thing here. Would this probability give reason to doubt a claim that rockets were able to be sold for more than 170 Doge apiece? Yes, since 0 is less than 0.05, I would doubt a claim that a random sample of 50 could be sold for less than or more than okay. So there we're using that p-value to conclude in kind of a masked way a little bit. And that is it. I would kind of expect that. I really think that sampling distribution is going to be pretty common to show up. It's one thing it seems to be favored a lot in the new CED, and it has shown up in the past as well, those type of questions. So describing a sampling distribution, same as describing a regular distribution, using your normal condition for shape, mean and standard deviation from your formula sheet, okay? And when you're doing a normal probability there, that sampling distribution is just really changing the standard deviation. Okay. All right. So that wraps it up. We skipped some multiple choice and free response there in the end. Thanks for sticking through the technical difficulties. Join us in the Discord channel if you have more questions. I'll try to answer some tonight, and make sure you're get those things answered as we work things on. Okay. Let's see real quick before we hop off here. All right, we can do this. We'll do this. All right. So I can't find my camera. I was going to share my camera. I just want everybody to know, like, you have worked super hard over the past few weeks, probably. Today on a Sunday afternoon, you hung with us for 5 hours or maybe 2 or 3 hours. But either way, that is a awesome achievement. You stuck through technical difficulties, of course. Anytime with technology, that's going to happen. And I think you have learned a great deal over this year. So go in tomorrow with some confidence as you go to take your test. You know things about AP statistics. There might be a question, a free response that catches you off guard, and you kind of panic because you don't know what to do. All right, calm down, take a deep breath, move on to the next one. All right. You will find common ground. You will find things that are familiar that we looked at today that you've studied all year. Okay, don't panic because of that one question. Like, you've got this. You have got this. You know what to do. You know what's going on. You have learned a great deal about statistics. And I always tell my students this going into the year. I want you, number one, I want you to be able to have a chance of getting college credit. Like, that's a great option for you taking an AP course. Number two, I want you to learn the rigor of a college course. And AP Stats is a very rigorous course in the way you write definitions. And we have come to that conclusion over the past few weeks. And then third, I want you to be able to learn when you can look at data and call out falsehood. Okay. I really want to say, calling someone out or whatever, but being able to look at it and say, hey, there's something off with this data. How was it sampled? How was people asked the question? All right. This sample, was it randomly pulled from all population or was it biased? And be able to, call out things when you see them. Okay. In the age of social media, data is thrown at you every single day, and a lot of it is complete crap. And I want you to be able to look at it and be able to call it when it's complete crap. Maybe I can say that. Okay. And I think you've learned to do that. Okay. I get emails back from students all the time, even when I was first teaching stats and didn't really know what I was doing. And they say, hey, I was in college and I was given this study and I read it and it was very suspicious. It was kind of sus. And I'm like, yes, you might not have passed the exam, but you got something out of it that you can look at a study, you can look at things being thrown at you and determine that something was up there. Okay. So that is what, one thing I really want you to be able to pull out of this course in any part. And kind of the last thing, okay, and then we will log off here, and I'm going to go eat some food because I'm hungry. And I didn't eat my Uncrustable. I set it out today to thaw from the freezer, and I never did eat it. But so anyways, yeah, there's my camera. Okay. Yes, I feel like I'm seeing you, and I wanted to be able to see you for this last little bit. You are not defined by your score. Okay. I have students I talk to, and they're like, well, what if I don't pass the exam? I feel like such a letdown. No, you are not a letdown. You have worked hard. You have persevered. You have, oh my gosh, this school year was absolutely insane for me. It included weeks of me being out, weeks of students being out, and it was crazy. You persevered through that. You deserve a burrito from your favorite burrito place for that. And be proud of the work you've put in. You're not defined by your score. I hope everybody is prepared. I hope everybody gets the score they want. But inevitably, that's probably not going to happen. But don't define yourself by your score. If you have to take stats in college, then okay, you're going to be well prepared because you took a really rigorous course in high school. And if you pass, and this is kind of a little note here, if you pass and your program that is not math related at all says you have to take pre-cal or finite or something like that, ask your academic advisor if they will accept AP Stats credit. I've had multiple students come to me and like, oh, well, I still have to take pre-cal. And then I'm like, no, ask your academic advisor if AP Stats credit works. And then it ends up working, and they don't have to take a math in college. So ask your academic advisor if you pass, hey, will this substitute for my math credit, even if stats is not the math credit they want to give credit for, okay? But yes, go out there, get a good night's sleep, eat you a good lunch tomorrow before you go and test, and knock this test out of the park. You are prepared. Be 99% confident with a large sample size, because we know the more confident you are, the more that margin of error has to increase. But we're going to counteract that large margin of error with a large sample size that's going to kind of make up for it. So go in there 99% confident that the true mean score that you will make tomorrow is between a 3 and a 5, because we're going to pass this exam. Great job today. Thanks for joining. You are all awesome. I am proud of every single one of you. Go make me even more proud tomorrow. Adios.